Imagine a force so powerful that it can form entire galaxies and yet remain hidden from view. The phenomenon of light trying to escape and time itself deforming. This is the reality of the supermassive black holes that lurk in the center of countless galaxies, including ours. But the story does not end there. It ends there. Recent discoveries have confirmed that these cosmic giants are not only passive consumers of matter, but influence the very structure of the universe, driving the formation of stars, shaping the evolution of galaxies, and even playing a crucial role in the creation of planets like Earth. Today we delve into the hidden mechanisms behind these forces and explore the revolutionary technologies that are finally revealing these secrets. What we have discovered could change our vision of the universe forever. So, first, making sure we are on the same page, let's discuss some theory. We start with the quasars, which are the energetic heart of active galaxies in the universe. These luminous beacons, powered by supermassive black holes that absorb large amounts of matter, eclipse the collective light of all the stars of their host galaxies. However, in our case, a particular subset of quasars known as red quasars has attracted the special attention of astronomers. Unlike their bluer counterparts, red quasars are wrapped in cosmic dust, which plays a key role in their unique characteristics. The red color observed in these quasars is a direct effect of the dust that surrounds them. The dust absorbs the shorter blue wavelengths of light and lets the longer red wavelengths through. This phenomenon not only changes their appearance, but also increases radio emission, as recent studies have shown using data from the Dark Energetic Spectroscopic Instrument, DESI, and LORE, which is a set of low-frequency antennas. A study by Victoria Fawcett and her team at the University of Newcastle has found that red quasars emit stronger radio signals than their dust-free blue counterparts. The intense radiation emanating from the quasar collides with the surrounding dust, exciting the molecules inside and causing them to emit radio waves. This interaction is key to understanding why red quasars are noisier on radio. But why are these red quasars so important? The answer lies in their age and evolutionary stage. Red quasars are believed to represent a younger phase in the life cycle of active galaxies. The dust that envelopes them is not just an obstacle, but a vestige of the galaxy's past, probably formed during an intense star formation event caused by galaxy mergers or other dramatic interactions. As the supermassive black hole continues to feed, its flow gradually blows away this dusty veil, revealing a blue quasar with a much weaker radio emission. This burst phase refers to the evolution of a quasar from a dusty and noisy formation to a cleaner and bluer quasar with attenuated radioactivity. The observation of red quasars offers astronomers a glimpse into the early stages of this transformation and provides valuable information about the mechanisms that govern the evolution of galaxies. The discovery of thousands of red quasars by the Fawcett team underscores their importance in the cosmic landscape. These objects are not just rare anomalies, but crucial pieces of the puzzle to understand how galaxies evolve as supermassive black holes grow. Just like their host galaxies, and quasar activity plays a central role in this dynamic process. Now that we understand the basics, we can continue our journey and delve into the concept of the burst phase and its impact on the evolution of galaxies. The burst phase theory provides a deeper insight into the life cycle of red quasars at the center of young active galaxies. This phase is believed to represent a critical period in evolution, when the supermassive black hole in the nucleus begins to clear the dense clouds of gas and dust that obscure it, transforming the galaxy from a red quasar to a blue one. This theory is based on the enormous force generated by a supermassive black hole that feeds on material from its accretion disk. The intense gravitational forces within this disk create friction that heats the gas to millions of degrees. This process not only illuminates the quasar, but also gives rise to energy releases that ultimately lead to the burst phase. These currents, consisting of high-speed winds and columned magnetic jets, act as space brooms that sweep away the surrounding gas and dust and collide with matter. These jets generate shock waves that further accelerate the cleaning process over time. This cleaning reveals the interior of the quasar, reducing the dust content and allowing the quasar to shine more intensely in the optical and ultraviolet wavelengths, a stage that we have already discussed and designated as a blue quasar. This theory is supported by observations made with space telescopes. The infrared capabilities of the JWST allow astronomers to penetrate the dust and obtain detailed images and data that reveal the dynamics of this burst phase. These observations reveal the interaction between the quasar jets and the surrounding matter, which is consistent with the process of expelling dust and gas from the galactic nucleus. These findings agree with the predictions of the burst phase theory and convincingly demonstrate that red quasars are, in effect, a transitional state. Okay, now, as an example, let's look at some news. It is not the first time, and here it is again. The James Webb Space Telescope has once again opened a new chapter in our understanding of the cosmos. Among its many discoveries, the case of the galaxy ESO 428G14, located about 70 million light-years away, stands out. An active galactic nucleus, or AGN, a region with a supermassive black hole in its center that has a profound effect on the surrounding space. ESO 428G14 is not just any galaxy. Its AGN is a source of intense radiation that spans the entire electromagnetic spectrum thanks to a supermassive black hole that devours matter at an extraordinary rate. This phenomenon generates enormous energy, making the AGN one of the most luminous objects in the universe. But what has captivated astronomers is the recent discovery of shock features in the clouds of dust and gas surrounding this black hole, an unexpected twist that is changing our understanding of how these cosmic giants interact with their environment. The prevailing theory assumed that the energy that heats the surrounding dust in the AGN came directly from the supermassive black hole itself. However, the JWST observations revealed something much more intriguing. The energy that heats the dust not only comes from the intense radiation of the black hole, but also from the violent interactions with the jets of gas ejected at speeds close to that of light from the poles of the black hole. These jets collide with surrounding matter, creating what astronomers now call shocks. These impacts have been a revelation. Previously, scientists had debated how AGNs transfer energy to their environment. The discovery that radio jets can cause so much damage to nearby dust and gas was unexpected. This discovery challenges assumptions and opens new questions about supermassive black hole dynamics. The implications of these discoveries are profound. By detecting the interaction between radio jets and the surrounding matter, the JWST has provided a clear picture of how supermassive black holes affect not only their immediate environment, but the entire galaxy. These jets, previously believed to be mere byproducts of black hole activity, now appear to play a crucial role in shaping their environment, affecting the rate of star formation and the overall structure of the galaxy. Therefore, this phase is a crucial element in the complex interaction between supermassive black holes and their host galaxies. To better understand the impact of active galactic nuclei on the surrounding space, study the feedback mechanisms that govern the interaction between supermassive black holes and their cosmic neighbors. It has long been known that at the center of many galaxies is a supermassive black hole surrounded by a dynamic and turbulent environment known as an active galactic nucleus, or AGN. The AGN is a region of intense radiation and powerful energy flows driven by an accretion disk, a chaotic and rotating structure of gas and dust that feeds the black hole. This disk, heated to millions of degrees under the action of enormous gravitational forces, emits radiation throughout the electromagnetic spectrum, from X-rays to radio waves. The accretion disk is not a homogeneous structure, but has distinct regions that behave differently depending on their proximity to the black hole. In the inner regions, matter rotates inward at incredible speeds, generating enormous amounts of heat and emitting high-energy radiation. However, recent observations have provided new insights into the outer edges of these disks. For the first time, Astronomers have observed the outer edge of an accretion disk, providing a clear picture of its size and structure using the James Webb Space Telescope and the Gemini near-infrared spectrograph. Near-infrared. The researchers detected emission lines in the near-infrared spectrum from the distant quasar 3C 273. These lines, broadened by the Doppler effect, revealed the size of the accretion disk, confirming its immensity and the turbulent conditions within it. The study suggests that these emission lines occur when atoms in the disk absorb energy and enter an excited state, eventually returning to a lower energy state and emitting light. The unique double-peaked profile of these lines, caused by the disk's rotation, allowed astronomers to measure the size of the disk and provided information about the behavior of matter under the influence of a supermassive black hole. But the accretion disk is not the only actor in the AGN theater. Radio jets emerge from the poles of the accretion disk, streams of charged particles accelerated to speeds close to that of light by the black hole's magnetic fields. These jets are not just byproducts, but powerful forces that shape the environment surrounding the AGN. By colliding with the surrounding dust and gas, they create shock waves that can affect the evolution of the entire galaxy. The interaction of these jets with the interstellar medium can trigger star formation in some regions and suppress it in others. This feedback mechanism, known as AGN feedback, plays a fundamental role in regulating the growth of galaxies, as it enriches the surrounding gas with heavy elements or expels it. These jets can dictate the rate of growth of galaxies, effectively controlling the balance between the birth and death of stars. Death of the stars. In addition, black holes exert their influence through tidal disruption events, or TEs, when a star gets too close to a black hole and is torn apart by its gravitational forces. This process, often referred to as spaghettification, causes the star to stretch and disintegrate, with some of its material falling into the black hole and the rest being ejected into space. Recent research has confirmed that not all stellar material is absorbed by the black hole, but that much of it is shot out, forming a huge spiral cloud of gas that can hide high-energy radiation, such as X-rays. This cloud, detected thanks to polarized light, offers a vision of the consequences of a TD when a black hole that can hide high-energy radiation, such as X-rays. This cloud, detected thanks to polarized light, allows us to glimpse the consequences of a TD when a black hole's appetite leaves a visible mark on its environment. But this dust is not just small particles floating in the vacuum, but plays an important role in shaping our understanding of the universe and contains key information about the processes that govern the cosmos. Cosmic dust, often regarded as mere space junk, plays a crucial role in the complex processes of the universe. Cosmic dust is mainly formed from the remains of stars and is composed of tiny micron-sized particles, comparable in size to the thickness of a human hair, and composed of elements such as carbon, silicon, and metals. These particles are not only produced by the phenomenon mentioned above, but also by various stellar events, such as supernova explosions, when dying stars expel their outer layers into space, or by the gentle release of matter by red giants at the end of their lives. The formation of cosmic dust is proof of the life cycles of stars. In the case of supernovas, the intense explosion scatters heavy elements throughout space, which eventually cool and condense into dust grains. Similarly, red giants, as they expand and lose their outer layers, contribute to cosmic dust by slowly releasing material into the interstellar medium. Subsequently, the dust can be incorporated into new stars, planets, and even life, making it a fundamental component of cosmic recycling. However, cosmic dust is not only a byproduct of stellar evolution, but has a profound effect on our observations of the universe. One of the most serious problems posed by dust is its ability to obscure our vision of celestial objects. Dust particles can scatter and absorb light, especially in the visible spectrum, making it difficult to see through dense clouds in areas such as the centers of galaxies or around active galactic nuclei. This obscuration is especially problematic when studying black holes and quasars, where the presence of dust can hide the most interesting features. However, as we have already mentioned, The JWST, with its advanced infrared capabilities, allows us to penetrate the visible range of the spectrum by observing in the infrared. The JWST can detect the we have already mentioned. The JWST, with its advanced infrared capabilities, allows us to penetrate into the visible range of the spectrum observing in the infrared. The JWST can detect the heat emitted by dust particles, as well as light from objects hidden inside or behind the cloud. As we continue to unravel the mysteries of space, the future is even more promising with the upcoming Nancy Grace Roman Space Telescope, which will launch in 2027 and complement the JWST by offering a wider panoramic view of the universe, capturing infrared images 200 times larger than those of Hubble, but with the same level of detail. The wide field of view of the Roman telescope will allow it to collect an unprecedented amount of data, providing information on billions of galaxies and helping create a three-dimensional model of the universe. This telescope will not only expand our understanding of cosmic dust and its role in the formation of galaxies, but also could answer some of the most important questions in astrophysics, such as the nature of dark energy and the structure of the universe, as well as on the largest scales, whether mapping the expansion of the universe or discovering new exoplanets. The future of space exploration offers endless possibilities thanks to these revolutionary technologies. We are on the verge of revealing secrets that will forever change how we see the cosmos. Stay curious and look to the sky, because the universe is full of mysteries waiting to be explored. Music. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and popular legends, it hides secrets that have eluded us for centuries. Among these mysterious features is the lunar South Pole, a region shrouded in perpetual shadow and intense cold. Intact, and without this, is the story of Chandrayaan-3, India's daring journey to unexplored territory. Launched on a journey of over 238,000 miles, Chandrayaan-3 embarked on a mission of discovery, not just distance. Its goal was to unravel the mysteries of the moon, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to navigate an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have intrigued scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. As Chandrayaan-3 ventured beyond Earth, it carried the aspirations of a nation and the curiosity of the world. Its main objective was clear, but difficult to achieve: a soft landing near the south pole of the moon, a feat that had never been achieved before. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the vacuum of space, overcoming the challenges of insertion into lunar orbit and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a mosaic of craters and mountains, many shrouded in perpetual darkness. The challenge was not just to land, but to do so safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram lander separated from the orbiter, its descent began. The lander, equipped with advanced sensors and engines, began its perilous journey to the moon's surface. Imagine a spacecraft autonomously navigating a maze of craters and rocks in search of terrain safe enough for landing. The systems on board the lander worked tirelessly, analyzing every inch of the terrain below. Facing this treacherous landscape, the lander also struggled against extreme temperatures. The south pole of the moon is a place of extreme contrasts. The sun barely rises above the horizon, while the shadows hide frigid temperatures that can drop to 382 degrees below zero. As the lander made its final approach, the hearts in the flight control center beat faster. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a slight bump, the Vikram lander, landed, marking a historic moment not only for India, but for lunar exploration. In the silence of the lunar South Pole, Chandrayaan-3 began its mission of exploration and discovery. Thus, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The objective of the mission was to maximize the study of the characteristics of the Moon, especially its exosphere and ionosphere, and to establish the range of temperature variations just below its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, it is so rarefied that it almost resembles a vacuum. The instruments of the Chandrayaan-3, developed with the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delves into the lunar ionosphere. This layer, formed by solar energy that ionizes the atoms of the exosphere, plays a crucial role in lunar communications and navigation. The measurements of Chandrayaan-3 were designed to provide unprecedented information on the density and behavior of the ionosphere, important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was the study of temperature variations just below the lunar surface using one of the lander's 4 instruments, the CHASTE, or Thermophysical Experiment of Chandra's surface. The temperature probe, submerged in the lunar regolith, had the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a strong contrast of temperatures on the surface during a lunar day. Temperatures rose drastically to 60 degrees Celsius. While at only 8 centimeters deep, they dropped significantly to minus 10 degrees Celsius, demonstrating that lunar soil is a potential thermal insulator. This discovery opened new opportunities for future lunar habitats, as it suggests that the lunar regolith could serve as a thermal insulator to protect astronauts from the harsh temperatures and harmful radiation of the Moon. These studies were more than just scientific endeavors. They were steps towards a future in which the Moon could be a gateway to further space exploration. The mission's results on the exosphere, the ionosphere, and the lunar subsurface temperature laid the foundation for understanding the Moon's environment and its potential to support human life. In the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon not observed in more than 50 years, a moonquake. The mission managed to shed light on one of the most intriguing and least understood aspects of the Moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument designed to detect the slightest tremors on the Moon, achieved it. Chandrayaan-3 detected what appeared to be a moonquake, a significant discovery, given that the last observation was during the Apollo missions in the early 1970s. Lunar earthquakes differ fundamentally from terrestrial ones. While the seismic activity of Earth is largely due to the movement of tectonic plates, the Moon, which lacks these plates, experiences earthquakes for various reasons. These tremors can last much longer than earthquakes, sometimes up to an hour. Their origin is of scientific interest. Data from Chandrayaan-3 suggest several possible causes for these moonquakes. One theory involves meteorite collisions, which could cause shock waves penetrating the lunar crust. Another reason is that the Earth's gravitational force causes tidal forces that load the lunar crust, and extreme temperature fluctuations on the lunar surface can ultimately cause expansion and contraction, leading to earthquakes. These moonquakes are not only superficial phenomena, but windows into the Moon's interior. By analyzing seismic waves, scientists can deduce the composition and structure of our satellite's interior, resembling an ultrasound of the lunar interior. This information is of great importance to understanding the Moon's formation and evolution. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened new perspectives on the geological processes that shape the Moon to unravel the geological mysteries of the Moon. The Chandrayaan-3 carried out another exploration, and, among the most intriguing findings, is the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes small samples of lunar soil using high-energy laser pulses. When the plasma emits light, The spectroscope analyzes its wavelength, revealing the presence of various elements, including sulfur. Sulfur's presence on the Moon is a significant finding. On Earth, sulfur is often linked to volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide information about the Moon's volcanic history and the processes that shaped its surface. Besides sulfur, another key objective of a Chandrayaan-3 mission was the search for water ice, a quest that has intrigued scientists for decades. Water ice on the Moon is not only a scientific curiosity, but a potential resource for future human missions, providing water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, did not find direct evidence of water ice on the lunar surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is that of the carbon trap, in which water vapor can migrate to permanently shadowed craters and freeze in the form of ice. The detection of sulfur adds another layer to this theory, since sulfur can become trapped with water ice and be released by the decomposition of water molecules from high-energy solar radiation. The lack of direct evidence for water ice raises important questions. Is the ice located deeper beneath the surface, protected from detection by the insulating properties of the lunar soil, or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the south pole of the Moon, the Chandrayaan-3 found more than just sulfur. The LIBS instrument of the rover performed the first in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each of which reflects part of the complex geological history of the lunar surface. Other measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its unique spectral signature, provided clues about the Moon's formation and its evolutionary history. Studies on the presence of hydrogen, a key component in the search for water. The discovery of these elements and the mission's ongoing search for water ice underscore the dynamic and complex nature of lunar geology. Each discovery, each unanswered question, brings us closer to understanding our closest celestial neighbor and prepares us for the next steps in lunar exploration. The Chandrayaan-3 mission to the south pole of the Moon opened a new chapter in lunar exploration and also paved the way for the next ambitious leap, the LUPEX Lunar Polar Exploration Mission, for its acronym in English. This joint venture between the Indian Space Research Organization and the Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the Moon's South Pole region. JAXA will likely provide the H-3 launch vehicle and the rover, currently under development, and ISRO will provide the lander. This mission represents important international cooperation in lunar exploration. The mission's objectives are multiple. It will demonstrate new surface exploration technologies, fundamental for sustained lunar exploration in the polar regions. Precise landings will be achieved through the use of a feature-matching algorithm and navigation equipment derived from JAXA's Intelligent Lander to investigate the lunar mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples at a depth of 15 meters. 5M. The search and analysis of water are key mission objectives, and the possible discovery of water ice could be a turning point for future lunar missions. Parallel to LUPEX, ISRO's Chandrayaan-4 mission, designed to bring samples from the Moon, is in the planning phase and is scheduled to launch in 2028. Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a reentry module. The planned mission's ambitious goal is to bring soil samples from the Moon, which will provide very valuable information about the lunar environment. The mission will involve complex maneuvers, such as sample collection, docking in lunar orbit, and the return of samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the moon's mysterious nature. These results provide crucial information about the moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration looks promising. Missions like LUPEX, Chandrayaan-4, based on the legacy of its internal structure and the potential for future lunar habitats. Looking ahead, the future of lunar exploration looks promising. Missions like LUPEX, Chandrayaan-4, based on the legacy of the previous ones, will continue to explore the mysteries of the moon. The role in these efforts is not only that of participant, but also that of pioneer. This event truly inspires us to look beyond the vast mysteries of the cosmos. In the infinite depths of a universe lies a key principle as mysterious as it is omnipresent. This force governs the very structure of existence, but remains hard to perceive for the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos on Earth. Entropy is evident in every leaf that whispers, in every wave that breaks, and in every cloud that drifts. It is the silent organizer of natural processes, from the simplest to most complex. But what really is entropy? It is a phenomenon often misunderstood as mere disorder, but it is more than that. Entropy is a transformation, a movement from order to disorder, from concentration toward dissipation. This is why coffee cools, why ice melts, why the scent of flowers dissipates in air. Let us understand, then, how order is hidden in what appears to be chaos, and how this mysterious force shapes our entire environment, from the smallest particle to the largest galaxy, and even the very course of life. There is a hidden force that acts in every corner of our world, from quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great workings of the universe. Imagine a drop of dew on a leaf, shining in the morning sunlight. As the sun rises, the dewdrop slowly disappears and its particles disperse into air. This phenomenon illustrates a fundamental principle of nature: the transition from a concentrated state, the dewdrop, to a dispersed state, water vapor, at the molecular level. This principle manifests as the tendency of particles to pass from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, going from structured gathering to scatter groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour fades as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it is far more nuanced. It is about transformation and change, like a sandcastle that slowly crumbles under relentless waves. Entropy is the inevitable transition from order toward disorder. This concept is summarized in the second law of thermodynamics, a principle of physics that states that in any closed system, entropy will remain constant or increase over the time. In other words, the natural course of the universe tends towards greater dispersion and disorder from the large scale of the cosmos, where stars and galaxies form and disappear, to the details of our daily lives. This principle is a universal constant that governs the birth and death of stars, the flow of rivers, and even the fading heat in a cup of coffee. Let's imagine a steaming cup of coffee left upon a table. Over time, its heat dissipates into the air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a diffuse state, cold room. Or think of an ice cube melting on a warm day. The solid and structured form of the ice becomes a puddle of water, whose molecules are now free to move. This transition from an ordered solid state to a disordered fluid state is a classic example of the increase of entropy in our universe. This silent but relentless force is always present, subtly directing the flow of energy in matter. As we delve deeper into the theory, it is essential to go back to the time when the concept arose. The story of entropy is intertwined with the minds of some of history's brightest scientists. Our narration begins with Sadi Carnot, a French physicist often considered the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His investigations laid the foundations for the laws of thermodynamics, which were later incorporated in the concept of entropy. Carnot's visionary work described how heat engines function and focused on how energy is transferred and transformed. His theories played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our history is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. Starting from Carnot's ideas, he delved into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot be spontaneously transferred from a colder body to a hotter one, a principle that underlies the second law of thermodynamics. His mathematical formulation of this concept made it possible to quantify it, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to the macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was revolutionary, as it showed that entropy can be understood as a measure of disorder at molecular level. His famous formula S equals K log W, where S is entropy, K is the Boltzmann constant, and W is the number of microstates, provided a deep insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundations for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. If we turn our gaze to the natural world, we find entropy present in all ecosystems, shaping the environment and the life that inhabits it. Nature, in its infinite complexity, is a vivid canvas of disorder and action. Let us consider a fallen tree in a forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi decompose it, returning nutrients to the soil. This process of decomposition and renewal is a manifestation of this principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting rock and soil and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of this principle's role in geophysical processes. The climate is another area in which entropy plays a crucial role. The formation of clouds, rain, thawing. All these are processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy manifests in the life cycles of marine ecosystems. Coral reefs, for example, thrive thanks to the delicate balance of nutrient cycles, temperature, and ocean currents, governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight to energy, is another interesting example. Here, entropy plays a role in the conversion of solar energy into chemical energy, a process so fundamental to life on Earth, from the tiniest interactions of microscopic organisms to the grandeur of ecological systems. This fundamental force is the invisible driver of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which entropy and order coexist in a delicate balance. Let us consider the simple process of the germination of a seed. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from its environment and converts it into structured and organized forms. However, the price to pay for this organization is an increase in the overall disorder of the system. In the human body, entropy is a constant companion. Our cells are energy conversion power plants that constantly transform nutrients into energy. This metabolic activity is vital to our existence, but also leads to an increase in disorder, as energy is released as heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates entropy's role in ecological processes. Each transfer of energy from one organism to another involves a dissipation of energy that contributes to the overall disorder of the ecosystem. If we look at the big picture, the evolution of life on Earth can be seen as a journey through entropy, from the first unicellular organisms to the complex web of life we see today. Evolution has been a process of increasing complexity driven by the fundamental laws of energy and matter. In the great narrative of life, entropy is not just a concept of decay or disorder. It is the driving force of growth, complexity, and a constant cycle of transformation. Life, in all its forms, thrives on the delicate balance between order and entropy, a testament to the profound interaction between energy and matter on the cosmic stage. The principles that govern entropy show a universe in constant motion, a scenario in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics inside clouds of gas and dust that collapse under gravity, heating up and eventually triggering nuclear fusion. It is a transition from potential energy to kinetic energy, a cosmic example of energy distribution on a large scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovas, scattering their elements throughout the cosmos. This dispersion is a powerful demonstration of a universe's tendency of a universe to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have a gravitational force so strong that not even light can escape from them, play an important role in the universe's energy dynamics. The event horizon of a black hole marks the point of no return where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is in itself a confirmation of these principles. Galaxies are separating. Energy is distributed more evenly in vast space, and the fabric of the cosmos is expanding, all of which indicates that the universe is evolving towards a state of greater dispersion. The cosmic background radiation, the afterglow of the Big Bang, allows us to glimpse the early universe as we know it. This radiation is a vestige of an era in which the universe was hot, dense, and in a state of lower entropy. Paradoxically, as the universe expanded and cooled, its entropy increased, and this led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the universe's thermal death. In this scenario, the universe reaches a state of maximum entropy in which all energy is distributed so evenly that new energy transformations become impossible. This is a future in which the universe is cold, dark, and empty of the energetic dynamic that drives cosmic evolution. In this vast cosmic scene, the flow and transformation of energy give form not only to the stars and galaxies, but also to the very destiny of the universe. It is a continuous process of creation, transformation, and disintegration. In the modern world, the concept of entropy has transcended its scientific origins and found applications in a variety of fields, subject to common erroneous concepts. Currently, entropy plays a crucial role in the development of advanced technologies in the field of renewable energies. A deep understanding of this concept is essential to improving the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge helps enormously to optimize the conversion of natural energy sources into usable energy. In information theory, entropy has acquired a new meaning. It represents a measure of the uncertainty or randomness in a system. This concept is crucial in the encryption and the compression of data, where it is essential to control and predict the information patterns. Despite its scientific importance, entropy is often misinterpreted. A common error is to equate entropy solely with disorder or chaos. And while the definition that entropy leads to an increase in disorder is correct, it is convenient to clarify that we are talking about the distribution of energy and the probability of certain states. Another error is the idea that entropy can be reversed or overcome. In popular culture, we see images of the inversion of time or the spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Research in modern physics is studying its impact on quantum mechanics, the behavior of black holes, and the final destiny of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand the patterns of urban development. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be fundamental to address them, whether to advance in technology, explore space, or manage our planet and conserve its resources. Entropy remains a fundamental concept that will continue to define our journey toward the unknown. Mercury is an enigmatic planet. Despite being the closest to the Sun, it remains the least known to us. Often eclipsed by its neighbors, it is a world of mystery that waits to be revealed. What if Mercury is not what we thought? Recent discoveries indicate that this planet is more dynamic and complex than anyone imagined, from landscapes that shrink to mysterious blue depressions. Mercury is challenging everything we know about it. Imagine a planet that revolves around the Sun at a dizzying speed, a world so close to the solar oven that it is difficult to even approach. Few missions have dared to visit this elusive world, and those that have done so have only uncovered some of its secrets. However, a new mission, Bepi, promises to reveal mysteries that have intrigued scientists for decades. We are already seeing things that defy all explanation: strange characteristics, unexpected phenomena, and clues of a story yet to be told. The X-ray auroras of Mercury, its changing topography, and its hidden interior suggest that the planet is much more intriguing than we ever thought. Prepare to see Mercury in a completely new light. It is not just a planet. It is a mystery in the confines of the Sun. Mercury, the innermost planet, is the one that orbits closest to the Sun. It is the smallest planet, slightly larger than our Moon, and it takes only 88 Earth days to complete an orbit. Due to its proximity to the Sun, Mercury experiences extreme temperatures that range from scorching highs of 800 degrees Fahrenheit to frigid lows of minus 290 degrees Fahrenheit during the night. Its surface is a mosaic of craters, mountain ranges, and plains. Unlike other planets, it does not have a significant atmosphere that protects it from meteorites, which results in a landscape heavily dotted with craters reminiscent of our Moon. One of the most striking characteristics is the Caloris Basin, one of the largest impact craters in the solar system. This enormous basin, about 960 m in diameter, was formed by a colossal impact in the early history of Mercury. Another unique aspect of Mercury is its unusually large core, which constitutes approximately 85% of the planet's radius. This iron-rich core generates a magnetic field, but it is only 1% as strong as Earth's. Despite its weak magnetic field, Mercury has magnetic poles and a magnetosphere that interacts with the solar wind, creating phenomena such as the recently discovered X-ray auroras. The exploration of Mercury presents significant challenges. Mercury's proximity to the Sun means that spacecraft must withstand intense solar radiation and extreme heat. In addition, Mercury's rapid orbit requires precise and energy-consuming maneuvers to enter its orbit. In 1973, NASA launched Mariner 10, the first spacecraft to visit Mercury. Mariner 10 used the gravitational assistance of Venus, which allowed it to perform 3 flybys of Mercury between 1974 and 1975. These flybys produced the first close-up images of the planet's surface, showing its heavily cratered terrain and complex geological characteristics. The spacecraft images showed a world similar to our moon, with vast plains and numerous impact craters. However, the mission only captured 45% of the planet's surface, leaving much more to explore. Despite the limited coverage, the mission's data formed a foundation for future research. Decades later, the Messenger spacecraft, launched by NASA in 2004, became the first spacecraft to orbit Mercury after a challenging journey that included flybys of Earth, Venus, and Mercury. The ship entered its target orbit in 2011. During its 4-year mission, Messenger made more than 4,000 revolutions around the planet, collecting a large amount of data on the composition of the surface and the magnetic field of Mercury. Messenger showed Mercury's surface in unprecedented detail, mapping almost the entire planet. It revealed volcanic plains, evidence of past tectonic activity, and offered a glimpse of Mercury's atmosphere. In its magnetic field, Messenger showed the surface of Mercury in unprecedented detail, mapping almost the entire planet, revealing volcanic plains, evidence of past tectonic activity, and offering a glimpse into the planet's thin planet's exosphere. One of the most surprising discoveries was the presence of water ice in permanently shaded craters at Mercury's poles, even though the planet is close to the Sun, building on the successes of Mariner 10 and Messenger. The Bepi-Colombo mission represents a major step forward in Mercury's exploration. The mission is a joint effort between the European Space Agency and the Japan Aerospace Exploration Agency, launched in 2018. Bepi-Colombo should provide comprehensive data on the geology, atmosphere, magnetosphere, and history of Mercury. Bepi-Colombo consists of 2 main spacecraft: the ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter, also known as MEO. Together, these spacecraft will study the planet from different perspectives, offering a holistic view of its environment and evolution. The Bepi-Colombo mission's journey to Mercury will be long and complex, involving many gravity-assist maneuvers. Bepi-Colombo has already made flybys of Earth in 2020 and of Venus in 2020 and 2021. It will perform 6 flybys of Mercury before entering orbit in December 2025. These flybys are critical for adjusting the spacecraft trajectory and reducing its speed enough to be captured by Mercury's gravity. The objectives of Bepi-Colombo are ambitious. The mission must map the planet's surface in high resolution, analyze its composition, and study the magnetic field and magnetosphere. It will also study the planet's exosphere, and look for evidence of volcanic and tectonic activity in the past. By comparing data from both orbiters, scientists hope to gain new insights into Mercury's formation and evolution, as well as its mysterious magnetic field. Since its launch in 2018, Bepi-Colombo has been progressively approaching Mercury, performing a series of flybys that have already yielded significant results. These preliminary observations provide new insights into Mercury's dynamic environment and complex geology. One of the mission's key contributions has been the detailed mapping of the surface of Mercury. The spacecraft has discovered many previously unknown craters, each telling a different story of the planet's turbulent past. Among them are impact basins that show the scars of ancient collisions, shedding light on the chaotic early solar system. One of them is the discovery of X-ray auroras around the planet. Unlike visible terrestrial auroras, Mercury's auroras are detected in the X-ray spectrum. This phenomenon was first suggested by the Messenger mission and has now been confirmed by Bepi-Colombo. These X-ray auroras are caused by the interaction between Mercury's magnetic field and the solar wind, a stream of charged particles emitted by the Sun. When these particles collide with the planet's surface, they generate X-rays that cause a faint but scientifically valuable glow. This discovery not only confirms the presence of a magnetosphere, but also provides information about the nature of Mercury's magnetic field and its interaction with the solar wind. Another important recent discovery was the confirmation that Mercury is still shrinking. High-resolution images have revealed features such as lobate scarps and wrinkle ridges, formed by the compression of the planet's crust as its core cools and hardens. These results are based on observations made by the MESSENGER mission and provide clear evidence of ongoing geological activity on Mercury. The compression of the planet has caused its radius to shrink several kilometers since its formation, creating tension cracks on the surface that manifest as ridges and cliffs. Bepi, in turn, has identified several regions where this contraction is most evident, offering a unique opportunity to study planetary geology in real time. These regions reveal not only Mercury's cooling history, but also its current state, providing scientists with clues about the. At first glance, Mercury's cratered surface resembles that of our Moon. Both bodies are plagued by impact craters, indicating a long history of collisions with asteroids. However, a closer look reveals some significant differences. Mercury's craters are often interspersed with ridges and fault scarps, less common on the Moon. These scarps are indicative of Mercury's compression, a process not observed on the Moon. In addition, there are areas on Mercury's surface with fewer rocks than on the Moon, suggesting different geological processes. One of Mercury's most enigmatic features are its hollows, first discovered by the MESSENGER mission. They are irregular and shallow depressions, often surrounded by bright halos. Their formation has baffled scientists since their discovery. Initially, researchers hypothesized that these depressions could be of volcanic origin. They considered the possibility that volcanic processes had left these unusual formations. However, the distinctive appearance of the depressions and the absence of associated volcanic features motivated further investigation. According to the current theory, the depressions of Mercury were formed by sublimation, a process by which solid materials are directly converted into gas. This process likely involves volatile compounds beneath Mercury's surface. When these volatile compounds sublimate, the surface erodes, forming the sinks and the bright halos that are observed around the depression. These data suggest that, despite its solar proximity, Mercury stores volatile compounds just below the surface. Continuous sublimation and the formation of depressions indicate that the planet remains a geologically active world. Contrary to what was previously believed, Mercury's proximity to the Sun and the extreme temperatures of its surface led scientists to believe that it lacked volatile compounds. However, recent discoveries have dramatically changed this view. High concentrations of sulfur, chlorine, sodium, and potassium have been found on the surface of Mercury, indicating the presence of layers rich in volatile compounds that extend several kilometers deep. The discovery of sublimation depressions with a flat bottom and a bright interior and a halo, indicates the existence of volatile compounds under the surface of Mercury. These depressions are formed when volatile materials sublimate, causing erosion of the surface and the formation of sinks. This ongoing geological process suggests that Mercury continues to lose volatile compounds, which changes our understanding of its geological history and its activity. Sublimation leads to another fascinating phenomenon on the planet, its sodium tail. Observations show that Mercury emits a tail of sodium atoms, making it similar, in a sense, to a comet. This phenomenon is caused by solar radiation and the solar wind, which launch sodium atoms from the surface of Mercury into space. The sodium tail extends millions of kilometers into space and is a clear indicator of the continuous release of volatile compounds from the planet's surface. This tail is not visible to the naked eye, but can be detected with specialized instruments, which allows us to learn a lot about the exosphere of Mercury and the processes that contribute to its formation. Interestingly, the volatile content of Mercury has been compared to some of the most extreme environments on Earth, such as the Atacama Desert in Chile. Both regions have high concentrations of salts and other volatile compounds, despite very different environmental conditions. The Atacama Desert is known for its extremely dry conditions and high salt content, supporting unique extremophile organisms thriving in extreme conditions. Research indicates that similar conditions may exist under the surface of Mercury, where salts and other volatile compounds may create niches for possible microbial life, although in much more extreme conditions. Atacama Desert extremophiles survive in very saline and dry conditions, suggesting parallels with possible habitable habitats on Mercury. These microorganisms have adapted to live in niches with minimal water and high concentrations of salt, suggesting that life could exist in similar conditions on Mercury if the planet has a subsoil rich in volatile compounds. It is also possible that this environment provides the necessary conditions for life, at least in microbial form. The presence of halides and other salts could lead to the formation of liquid water through a process of deliquescence, in which salts absorb moisture from the atmosphere, even in small amounts, which could support microbial communities. The origin of Mercury has long been an enigma for scientists. According to traditional theories, it formed not far from its current position. However, considerable recent research agrees that Mercury could have begun its journey much farther from the Sun. One main theory is planetary migration, according to which, in the early solar system, gravitational interactions caused significant changes in planetary orbits. Mercury could have formed in the outer solar system, rich in volatile matter, and migrated inward over time. Evidence supporting this theory comes from Mercury's unusual density and large iron core. According to recent studies, the core of Mercury represents approximately 85% of its radius, much more than that of any other terrestrial planet. Some scientists speculate that Mercury was once a much larger planet, similar in size to Mars, with a thick mantle and crust. A catastrophic collision with another large body could have stripped Mercury of most outer layers, leaving behind a dense core and thin mantle. This hypothesis would explain the high density of Mercury and the presence of high levels of some elements such as thorium and potassium, which are commonly found in the depths of the interior of the planets. The giant impact theory is supported by Mercury's geological characteristics. The planet's surface is marked by impact craters and basins, such as the Caloris Basin, one of the largest impact structures in the solar system. This collision theory aligns with observations of other celestial bodies and their histories. Similar collisions are believed to have led to the formation of the Moon and caused significant changes in other planets, suggesting that the history of Mercury could be part of a broader pattern of planetary evolution in the solar system. The discovery of bonanite, a rare type of volcanic rock on Mercury, is also intriguing evidence. Bonanite is typically rich in magnesium and poor in other elements, indicating it formed under special conditions associated with high temperatures and pressures. Geologists have found similar rocks in Cyprus, suggesting a common formation process. They appear white in the images because the bonanite oxidizes in A. These terrestrial analogs provide information about Mercury's volcanic history and support the idea that its mantle has undergone significant melting and differentiation. In Cyprus, bonanite is associated with ancient tectonic processes when the oceanic crust was pushed into the metal and partially melted. The presence of similar rocks on Mercury suggests it has also undergone intense geological processes, possibly related to a hypothetical major collision and subsequent migration. By comparing the geological formations of Mercury with those of the Earth, scientists can reconstruct the history of the formation and evolution of Mercury. Characteristics such as faults, mountain ranges, and volcanic plains on Mercury resemble those of tectonically active regions on Earth. These comparisons show that, despite its small size and solar proximity, Mercury has a dynamic and complex geological history. The study of the geology of Mercury not only helps us understand its past, but also provides us with information about the processes that have shaped other rocky planets in our solar system. As Baecolombo approaches its destination, scientists eagerly await the wealth of data it will provide. It is expected that the missions will provide detailed maps of Mercury's surface, study its magnetic field, and offer new insights into its geological history. Although life is unlikely to be found on Mercury, the discovery of volatile substances and possible underground environments offers intriguing possibilities. Earth's extremophiles thrive in hostile environments, suggesting that similar life forms could exist on Mercury if the conditions are right. Mercury occupies a unique place in planetary science within the broader context of solar system studies. This planet is key to unraveling the history and evolution of terrestrial planets. Its study helps us understand the processes that have shaped not only our solar system, but perhaps the rest of the solar systems. We look forward to the next wave of discoveries. Mercury promises to remain at the center of scientific research, offering endless opportunities to learn about the universe and our place in it. Beyond the reach of traditional microscopes and within theoretical physics lies a frontier not so much of remoteness as a possibility. And understanding this frontier is a challenge not because of physical barriers or great distances, but because of the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the basic components of reality and technology behave very differently from anything we have encountered in our macroscopic world. Quantum mechanics is a term that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in multiple places at once, can spin in opposite directions at the same time, and can be entangled across the infinity of space, acting in unison without apparent connection. These strange behaviors are at the heart of a technology that could revolutionize our world. Quantum computing, at the center of this technological storm, is a concept so revolutionary and difficult to understand that it challenges our very perception of information and reality. As we travel through the quantum frontier, we enter a space where information is not only processed, but exists in states that defy classical logic. Here, quantum bits, or qubits, can store many possibilities at once, compared to the simple bits of current digital devices. But how do we preserve information in a system that loses its essence at the slightest interaction with the environment? Scientists may have some answers to that question, because quantum mechanics not only redefines computing, but encourages us to rethink the cosmos, intertwined with the fabric of space and time and enigmatic phenomena, such as black holes. These cosmic anomalies are not mere objects, but the key to understanding the quantum enigmas that hold the secrets of the universe. Join our expedition, an expedition to the frontier of the exploration of quantum mechanics that could ultimately redefine the meaning of computing, data protection, disease cure, and perhaps the understanding of the very structure of reality. Thus, you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, in which data is processed as a linear series of zeros and ones. In contrast, quantum computing works with qubits, which can represent zeros, ones, or both at the same time, using special properties of quantum mechanics to perform complex calculations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in the development of quantum computers is creating and maintaining quantum memory. Unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause decoherence of quantum information, known as quantum states, that has erased the stored data. It's like trying to keep a coin spinning on its edge. This susceptibility stems from the fundamental nature of quantum memory. It is not simply about storing data, but about preserving complex quantum states, which are the basis for the potential of quantum computing. Herein lies the paradox, the heart of quantum computing, the no-cloning theorem. This theorem is a unique rule of the quantum world, stating that it is impossible to create an exact copy of an unknown quantum state in the everyday world. If you want to avoid data loss, you can make copies, but in quantum computing it is impossible to make an exact copy of a qubit containing unknown information. This rule is a serious obstacle, as it means that traditional data protection and error correction methods, such as backups, simply do not work in the quantum realm. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They use quantum error correction techniques that involve entangling qubits, linking them together in complex ways, and allowing the system to detect and correct its own errors without having to directly measure the quantum state. These methods not only preserve information, but also preserve the very essence of quantum behavior. But how can gravity wells, where not even light can escape, and quantum computing be related? The intriguing connection between black holes and the burgeoning field of quantum computing begins with a profound mystery that they both share. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed revolutionary ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma. What happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to the problems of quantum computing with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So, how much information can a black hole store? Bekenstein, in turn, presented the concept that the entropy of a black hole, that is, its information content, is proportional not to its volume, as one would expect, but to the area of its event horizon. But how can a surface store information? After all, you need some kind of structure. You need atoms or something else that can store bits of information. Well, it turns out that you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck units are the smallest measurable scales in the cosmos. These units, named after Max Planck, mark the limits beyond which classical theories of gravity begin to crumble and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the smallest dimensions imaginable. So, why is the information content of a region of space equal to the surface surrounding that region and not its volume? Let us consider this analysis to better understand the unconventional way that information is stored inside a black hole. Let's imagine that our room is not just a library, but a magic one where our entire collection of books can be encoded simply on the wallpaper covering the walls. Instead of measuring the volume of the room to determine how much it can contain, we look at the surface area of the walls. This radical idea reflects how black holes store information, not in their vast void, but on their outer surface, like its event horizon. This leads us to the holographic principle, which may seem like science fiction, but is a serious scientific theory inspired by black hole thermodynamics. A hologram, in colloquial terms, is a flat surface that contains all data necessary to display a three-dimensional image. If we apply this to the universe, a surprising possibility arises. Everything you see around you, from your coffee cup to the stars in the sky, could be a projection of information encoded on some distant two-dimensional surface. The model of a Meson, known as the anti-de Sitter conformal field theory, or AD-CFT, goes further and proposes that the type of universe described by Einstein's theory of gravity, with negative and seemingly unlimited curvature, could be equivalent to a quantum theory of fields without gravity. It defines the boundary of that space. Essentially, it is as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring within it. This revolutionary idea suggests that our understanding of space and time, however intuitive it may seem, could be an emergent phenomenon of a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic storage of data observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing tasks impossible for classical computers. As we approach the domain of quantum computing, its impact on our future is becoming increasingly clear and very promising. This technology not only increases the speed of data processing, but also expands our ability to solve problems that were previously considered unsolvable. Cryptography, medicine, and space exploration are just the beginning in the field. Quantum computing is a double-edged sword. On one hand, it poses a significant threat to existing encryption methods, since traditional security protocols are based on the complexity of factoring large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods may become obsolete over time, leaving data vulnerable, from your personal correspondence to access to your bank account. However, this same capability opens up the potential for quantum cryptography, which can provide a fundamentally unbreakable level of security. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to intercept quantum keys changes their state, thus revealing the presence of an attacker. This method could revolutionize the transmission of confidential information, making our data secure even against the most sophisticated attacks. In medicine, the impact of quantum computing could be truly revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and costly process that often takes more than a decade. Quantum computers can significantly accelerate this process by predicting the properties of complex molecules and their interactions with the human body with greater precision than ever before. An interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung, allowing researchers to observe how drugs interact with human tissue in real time. Let's imagine a world in which we can model the human body in detail on quantum computers, creating digital twins that doctors can use to test treatments tailored to each patient. This approach could not only accelerate the development of new drugs, but also greatly improve their efficacy and safety. It represents a shift towards more personalized medicine, in which treatments are optimized for each patient's unique genetic characteristics. Unique genetic characteristics of each patient. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across all sectors. Its ability to solve complex logistical problems and optimize systems can lead to a more efficient use of resources. For example, quantum algorithms have already improved the movement of goods in the port of Los Angeles, increasing performance and reducing energy consumption. Space exploration can also greatly benefit from quantum computing. Navigating the vast expanses of space requires processing large amounts of data for the trajectory alignment system, diagnostics, and life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation and preserving critical satellite infrastructure. Research on black holes and quantum mechanics is not just a theoretical matter. It is shaping the tools that we hope will revolutionize our future. The knowledge gained from studying these cosmic mysteries is helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research to the unexplored confines of the cosmos. Thus, in simple terms, quanta are the smallest possible units of any physical property involved in an interaction, such as energy or matter, like particles and photons. In classical physics, everything seems fluid and continuous, but at the quantum level, things like energy move in small discrete packets. That is quanta, and that is why there are several different methods of quantum computing, each of which explores unique approaches to using these tiny units in order to generate enormous computing power. One of the most advanced techniques in current research on quantum computing involves superconducting circuits. Companies like Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures close to absolute zero, allowing quantum states to persist long enough to perform complex calculations. Another well-known method uses trapped ions and qubits. Companies like IonQ and Quantum use this technique, in which ions are held in space by electromagnetic fields and manipulated with lasers to perform quantum operations. This method offers longer coherence times, which means that quantum states remain stable for longer, although the operating speed is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum with qubits encoded using photons, particles of light. This approach, promoted by companies such as Xanadu and startups affiliated with academic groups, operates at room temperature and uses the properties of light to perform quantum computing. Recent advances include the development by Xanadu of a Borealis chip that uses a novel method to manipulate groups of photons in order to obtain quantum advantages. Quantum intertopological computing, which has emerged from a more theoretical framework, offers a new approach to using Chu particles, which arise from interactions within a material. Microsoft has been a key player in this field, exploring ways to create and manipulate these quasiparticles to create qubits that are naturally immune to external disturbances, which could solve the problem of quantum decoherence. In addition, a revolutionary approach to quantum computing is rapidly gaining momentum. This new method, using atoms held with optical tweezers, represents a significant advance in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative technology to discover how it has potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are not in or nothing new in physics, but their application in quantum computing is a new and rapidly developing frontier. By using ERS lasers to capture individual atoms, scientists create qubits less susceptible to interference and easier to control than with traditional methods. This technique is based on the unique properties of atoms, which are small and electrically neutral, allowing them to naturally avoid mutual interference that interferes with other types of quantum bits. This reduction of noise and interference is crucial for maintaining the coherence of quantum information, a constant challenge in quantum computing. A recent advance in February of this year has been the use of microlens arrays that allow significantly increasing the number of atoms that can be manipulated simultaneously. These arrays allow precisely arranging thousands of atoms in a regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange over 1,000 atoms with extraordinary precision. These atoms are not only kept static, but dynamically controlled, ready to perform complex quantum operations. The term breakthrough accurately describes the improvement that this method brings to quantum computing. By aligning two layers of microlens arrays and superimposing laser traps, scientists create a dense network of atomic qubits. This arrangement not only increases the initial number of qubits, but also improves their stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows addressing and manipulating each qubit individually, opening the door to complex and large-scale quantum algorithms previously unattainable. When comparing these new methods with existing technologies, such as superconducting qubits and ion traps, the approach of atoms and tweezers offers advantages in scalability and error reduction. Its ability to rapidly scale to thousands of qubits makes it a formidable competitor against better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation, but a realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing solving complex problems from cryptography to material science. As we conclude our journey through the quantum frontier, we are at a crucial moment in which quantum computing is moving from theoretical research to practical applications. The X Prize Quantum Applications Competition summarizes this transition, presenting a challenge with a significant incentive of $5 million to drive innovations that apply quantum computing to real-world problems over the next 3 years. Teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, materials science, energy, and other fields. This initiative not only accelerates the development of quantum technologies, but also highlights the potential of quantum computing to solve humanity's most pressing problems, expanding the limits of quantum computers. X Prize aims to stimulate the transition from experimental quantum applications to everyday tools, making the field of quantum mechanics accessible and useful to society at large. You've probably heard of dark matter, that elusive substance that makes up about a quarter of the universe, that ghostly puppeteer that pulls the strings of galaxies without ever showing itself. But dark matter is just the tip of the iceberg. Imagine a universe in which the balance of gravity is tilted in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the laws of gravity established by Newton and Einstein. What if their equations were not definitive? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the verge of a paradigm shift? Is our vision of the cosmos not as stable as we thought? In Cosmic Ball, the stars are the protagonists that call our attention. But have you ever wondered how these celestial bodies form? It all begins in the dark and cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, attracting the particles closer and closer until they stop resisting gravity and merge, triggering a nuclear fusion reaction that gives rise to a star. However, the life of a star does not last forever. There comes a time when the nuclear fuel runs out and the star faces its inevitable demise. For massive stars, this ending is spectacular. A supernova explosion that eclipses entire galaxies, even if only for a brief moment. These supernovas are not just cosmic fireworks. They're the forges of the universe. In the crucible of these explosions, elements heavier than iron are created. So the gold in your jewelry and the calcium in your bones are stardust, the remains of a supernova explosion. But this is where the plot thickens. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scenario. Dark matter, with its gravitational force, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without it. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a greater number of supernovas. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Modified Newtonian dynamics enters the scene. This theory suggests gravity behaves differently at very small accelerations. If Mond is right, the high rate of star formation in galaxies rich in dark matter could have an alternative explanation: binary stellar systems. Those cosmic pairs that we discussed earlier can serve as an ideal test laboratory for these theories. Its orbital dynamics can show if Newtonian gravity persists or if Mond offers a better explanation. As scientists delve into the data, especially the treasure that the Gaia mission has provided, we are increasingly close to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often represented as a silent, mysterious entity that shapes galaxies, but remains difficult to detect. One of the most compelling theories that attempts to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, meaning its particles move much more slowly than the speed of light. This slowness allows them to cluster together, forming the gravitational scaffolding on which galaxies are built. Computer models based on CDM have successfully reconstructed the large-scale structure of the universe. They show a cosmic network of galaxies connected by filaments of dark matter that is very similar to what we observe. But as in any good story, there are unexpected twists in the plot. While CDM does an excellent job explaining the grand architecture of the universe, it falters when we look closer at individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should decrease drastically as we move away from the center, but observations tell a different story. The rotation curves remain surprisingly flat, suggesting something more is involved, perhaps another type of dark matter or even a modification of gravity. And then there are the dwarf galaxies, smaller satellites of larger galaxies like our own Milky Way. The CDM model predicts many of these dwarf galaxies, but we do not see as many as expected. These inconsistencies have led scientists to consider alternatives and to question the very basis of the CDM model. Could it be incomplete or as many as expected? These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where MOND comes on the scene again, offering a different set of equations that better explain these galactic characteristics. It's as if there were two different scripts for the same movie, each with its own interpretation of the main character, dark matter. The scientific community is divided. Is CDM the definitive theory that unifies our understanding of the universe, or is it just a step towards a more complete model? For centuries, Sir Isaac Newton's equations have been the basis for our understanding of gravity. They have been tested, repeated, and verified, and have stood the test of time. But what if there is more? We present MOND, or modified Newtonian dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as in the outskirts of galaxies. The goal of MOND, conceived by physicist Mordechai Milgram in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those enigmatic rotation curves that we have previously discussed. As you can see, MOND fits perfectly with the flat rotation curves observed in galaxies without resorting to dark matter. It's as if MOND is telling us, wait, maybe it's not necessary to invest in a mysterious form of matter. Maybe you just have to adjust the equations. And it's not just about rotation curves. MOND has also managed to explain the dynamics of some galaxy clusters and even the large-scale structure of the universe without resorting to mysterious dark matter. But of course, no theory is without its problems. While MOND is successful in some areas, it faces difficulties in others, such as explaining the cosmic microwave background. The afterglow of the Big Bang, the cosmic microwave background, or CMB, is a snapshot of the universe only 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the characteristics of the remnant radiation well. However, MOND has difficulties in this aspect, and let's not forget our celestial pairs, the binary stellar systems, whose recent studies, some of which we have already discussed, have shown contradictory results when applying MOND to double stars. What does this bring us? At a minimum, a state of exciting uncertainty as new data arrives, especially from the Gaia mission. MOND continues to be the subject of heated debate. Is it the missing piece of the puzzle that will finally explain the anomalies we observe, or is it a useful, but ultimately flawed, stepping stone towards a more complete theory in a universe full of questions? Sometimes the answers are found closer to home. Just 15 million kilometers from Earth, Gaia orbits, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is not just any telescope, but a space cartographer mapping the positions, distances, and movements of over 1 billion stars with unprecedented precision. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with an amazing level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation that involves observing a star from two different points in its orbit. Gaia can triangulate the distance to stars with incredible precision. But Gaia is more than just a space explorer, it is a theory checker. Remember those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under a microscope. Let's take, for example, double star systems. These systems are crucial for testing theories, such as that of M. The precise measurements of Gaia of the positions and speeds of these stars can help us to understand which theory is the correct one, and they are not only stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data has been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. The measurement of the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yield slightly different values, and the data from Gaia became an important piece of this cosmic puzzle. But the Gaia mission is not without challenges. While the spacecraft provides a large amount of data, interpreting it is another story. The same data from Gaia has been used both to support and refute theories such as CDM and MOND, which has given rise to heated debates in the scientific community. It is like a high-resolution photograph in which everyone sees something different. Is it a speck on the lens or a revolutionary discovery? The interpretation depends on sophisticated statistical methods and, of course, on our basic hypotheses about the universe. There is nothing more fascinating than double stars. Two stars united in a gravitational embrace that orbit one around the other in a delicate balance of attraction and repulsion. As we mentioned previously, these dual systems are not only celestial spectacles, but cosmic laboratories in which, in the intricate ballet of their orbits, we can test our deepest theories about the very nature of gravity. Double stars have been a cornerstone of astronomical research for centuries. They have helped us to measure the mass of the stars, to understand stellar evolution, and even to confirm Einstein's general theory of relativity in the context of our current debate between cold dark matter and modified Newtonian dynamics. Double stars play an even more important role. Their orbital dynamics can reveal if Newtonian gravity persists or if MOND offers a better explanation. Recent studies have delved into this question. Some studies using data from the Gaia mission have shown that double star systems behave as Newtonian gravity predicts, which calls into question the applicability of dark matter theory. However, other studies tell a different story. They suggest that MOND is more suitable for some binary systems, especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct, or that we are missing a key piece of the puzzle? The scientific community is divided, and with reason, there's a lot at stake. The behavior of binary stars could confirm our current theories or make us start from scratch again in our search to understand the universe. So, how do we weigh the evidence? Let's get to know Bayesian statistics, a mathematical framework that could tip the balance, named after Thomas Bayes, an 18th century statistician and theologian. Bayesian statistics offers a way to update our beliefs in light of new data. It is like a mathematical expression of the scientific method itself. It works like this. One starts from a prior belief, or prior, which is the initial hypothesis. As new data becomes available, it is updated before formulating a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, whether it is cold dark matter, MOND, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is most likely given the observed information. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND or Newtonian gravity is the correct theory. It is not only about fitting curves, but about estimating the weight of the evidence, and it does not only apply to double stars. Bayesian statistics has been applied to a wide range of cosmic phenomena, from the distribution of dark matter in the CLERS galaxies to the expansion rate of the universe. However, Bayesian methods are not without criticism. One of the most controversial points is the choice of prior. That is, how to choose the initial hypothesis so that it does not distort the result. The choice of prior can be controversial because it can affect the results. If the prior leans heavily toward a theory, a posterior can confirm that theory, even if the other is equally true. As we struggle with these questions, Bayesian statistics remains a powerful tool in our analytical arsenal. It offers a way to make sense of complex data, filter out the noise, and find the signal. The universe seems to refuse to reveal its secrets easily, even as we collect more data. The debate about the true nature of gravity is intensifying. Hu Han, an astronomer who recently made headlines, said, "I felt like I was dreaming. It seems so unreal. It is because my results did not match any previous result." Chase's work stirred the waters by suggesting that When the gravitational acceleration of stars in certain double systems falls below a certain threshold, they are more consistent with MON models than with the standard gravity model. But here is the problem. Chase's findings contradict several previous studies. He mentions, a group has been claiming an anomaly for some time, but the anomaly did not seem to fit well with the predictions of existing modified gravity theories. This discrepancy in the results is not just an error, but a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does this bring us? Well, at least a state of productive confusion, as Chase concludes. Since standard cosmology is based on general relativity, cosmology needs a major revision. The debate is far from over. As we collect more data and refine our theories, the search continues for the ultimate truth about gravity and the universe. And in this search, each anomaly adds a new level of complexity and wonder. Saturn has captivated human imagination, from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. The mystery only deepens. Saturn has long been a symbol of the unknown and the mysterious. Its iconic rings have been the object of wonder and speculation since the time of Galileo. But what if we told you that these rings, as eternal as they seem, are actually a fleeting, cosmic phenomenon? Adding to the intrigue is a storm twice as wide as Earth with a mysterious hexagonal shape that is unleashed at Saturn's North Pole. What forces created such a geometrically perfect formation? But the mysteries do not just end there. Titan and Enceladus offer conditions that could harbor life. Lakes of liquid methane and geysers launching water and organic matter into space make these satellites more than just celestial bodies. They are possible homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who pointed his telescope at Saturn for the first time in 1610. What he saw left him perplexed, a planet with something like ears. He did not realize he was seeing the edges of Saturn's rings, a feature that would baffle astronomers for centuries. Galileo's telescope was primitive, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Entering the modern era, we saw the Pioneer 11 mission, the first spacecraft to fly by Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were previously inaccessible to terrestrial telescopes. But it was the Cassini mission that truly revealed Saturn in all its splendor. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings and its satellites, from the discovery of columns of water ice in Enceladus to the capture of the ethereal beauty of a hexagonal storm at Saturn's North Pole. Cassini revolutionized our understanding of this distant world, and here is an interesting fact. Long before the arrival of telescopes, the Maori of Nueva Zelanda had myths that described Saturn with a pararo, or belt, around it. How they knew it remains a matter of debate and speculation. But as we will see later, Saturn hides more than one mystery. What do you think could have created a hexagonal storm with a surface larger than Earth itself? Saturn is home to a geometric enigma at its North Pole, a six-sided storm that has baffled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep, lasting mystery that breaks knowledge about fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it was not until the Cassini mission, which orbited Saturn between 2004 and 2017, that we were able to see this cosmic spectacle firsthand. Cassini's images showed a symmetrical jet stream surrounding the vortex in the center of the hexagon. Unlike Earth's weather, Saturn's hexagon is a masterpiece of geometric precision. So, what causes this hexagonal storm to form? Researchers at the Universidad de Harvard have developed a 3D model that suggests that deep thermal convection in Saturn's outer layers could be to blame. This model shows that the storm could extend thousands of kilometers into the depths of Saturn's atmosphere, far beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory environment. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a vision of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from the planets of the terrestrial group. The hexagon's longevity is another mystery, as it has been observed for at least 4 decades, and possibly longer. This stable feature suggests that whatever feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let us now turn our attention from the mystery of the hexagon to another wonder of Saturn, its rings. More than just a celestial jewel, they're dynamic systems in constant change that interest both astronomers and the general public. But what are these rings made of, and why are they so ephemeral? Saturn's rings are mainly composed of water ice, with a mixture of dust and rocky material. Their size varies from tiny particles to huge chunks the size of houses. These ice particles are not static, but are in motion under the influence of Saturn's gravity and the attraction of its satellites. The rings are divided into subdivisions and gaps, each with unique characteristics. The most notable are the A, B, and C rings, separated by gaps, such as the Cassini division, a 3,000-mile gap between the A and B rings. The origin of Saturn's rings has long been debated. One theory suggests that they formed from the remains of shattered moon. Another theory claims that they are the remains of material from the solar system's formation, captured by Saturn's gravity. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of the dust contamination of Saturn's rings. They do not last forever, but are slowly disappearing due to a phenomenon known as ring rain, where particles from the rings are attracted to Saturn's atmosphere. This process is accelerated by micrometeorite bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict the Saturn rings will disappear in 100 million years. The depletion of the rings would not only change the appearance of Saturn, but could also have consequences for its atmosphere and its magnetic field. By stopping for a moment, we realize that even the most fascinating characteristics of our universe are not immune to the inexorable forces of physics, doomed to disappear in the chronicle of eternity. Saturn, the ring giant of our solar system, is not only a celestial wonder, it is also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Encelado, have fascinated scientists and have raised the debate about the possibility of life beyond Earth. Titan is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what is truly surprising is the speed at which Titan moves away from Saturn, 100 times faster than previously thought, which is an astonishing 43 centimeters per year. This rapid drift suggests a dynamic, evolving relationship between Titan and Saturn. Could this drift affect the internal dynamics of Titan, and perhaps even its potential for the existence of life? An atmosphere rich in organic compounds, such as nitrogen and methane, and the possibility of an underground ocean make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life be like in an environment radically different from Earth's? And let us remember Encelado, another Saturn satellite very different from Titan. It is an icy world with a highly reflective surface that outshines any other body in the solar system. Encelado takes the concept of an oceanic world to a new level. Not only does it have an underground ocean, but it also expels it into space, where a space probe can collect samples. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water that springs from hydrothermal vents. Hydrothermal vents can provide the conditions necessary for life, as we know it on Earth. We know on Earth, these sources teem with life forms that thrive in extreme conditions. Could Enceladus sources harbor similar, but alien, life forms? Enceladus also contributes to Saturn's Z-ring, a unique feature that further enriches the dynamic relationship between the Moon and its host planet. The icy particles of this ring open a window to the internal chemistry of the Moon, providing clues that could reveal its secrets. Titan and Enceladus are two moons that orbit the same planet, but are very different in their characteristics. Both present compelling arguments for the possibility of life, fueling our curiosity as we contemplate the possibilities of life on Saturn satellites. It should be noted that our curiosity is not limited to telescopes and computer models. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, scheduled to launch in the 2030s. This helicopter will fly over Titan's varied terrain, from dunes to impact craters. Dragonfly's main objective is to search for the basic components of life. It will analyze complex organic compounds in the atmosphere and on the surface and provide invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the Moon's geological processes and how they relate to its potential to harbor life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although there are currently no planned missions to Enceladus, the Moon's potential for life has made it an ideal candidate for future exploration. Scientists are proposing missions that could fly through Enceladus' plumes and take samples directly from its underground ocean. Such a mission could analyze the plume's chemistry for signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus' oceans adds another layer of intrigue, suggesting an environment in which life could thrive despite the technical challenges. A mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence of the existence of extraterrestrial life, or at least clues about the conditions necessary for life, music, to exist. As we have mentioned, Saturn's rings are not eternal, as was thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade. But how important is this for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mainly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle, but a torrent that carries water in quantities equivalent to an Olympic swimming pool every half hour. The mystery is compounded by the relative youth of Saturn's rings, since, although Saturn is about 4,600 million years old, data from NASA's Cassini mission suggests that the rings may be only a few hundred million years old. This leads us to wonder if Saturn's rings are so young. What catastrophic event could have led to their formation? The destruction of a moon, or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. For 13 years, it has collected 163 dust particles from outside the Saturn system. Surprisingly, the rings turn out to be quite clean, suggesting that they have not existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why have they not collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It is as if the rings were in a cosmic laboratory or a clean room isolated from the dust that permeates the rest of the solar system. As the rings deplete, Saturn's appearance will undergo a dramatic transformation. These rings have been the task of the planet, and their disappearance would not only change the appearance of Saturn, but could also have unknown consequences for its atmosphere, even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making this a topic of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to that of its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. The rings and satellites of Saturn are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can state without a doubt that the fate of one may shed light on the mysteries of the other. As we continue to study these celestial bodies, we can state without a doubt that the fate of one may shed light on the mysteries of the other. In the midst of the peace and tranquility of the celestial bodies of the solar system, there's an object that greatly disturbs the peace of the rest. The moon Io, different from any other that orbits around mighty Jupiter, shrouded in mystery. Io is a world of fire and fury, a stark contrast to the icy moons and tranquil planets that share its cosmic neighborhood. This mysterious moon, the most volcanic in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, plagued by hundreds of active volcanoes, tells the story of the relentless complexity of Jupiter's gravitational pull and other moons. Meet Juno, NASA's intrepid explorer on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and discover the secrets that have long remained hidden beneath its tumultuous surface. As Juno approaches closer than in the last 2 decades, we find ourselves on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's active volcanoes? How does this moon's turbulent nature affect the giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new views of space. Juno, a spacecraft made not only of metal and circuits, but also of ambition and curiosity, embarks on a journey that has not been made in more than 2 decades. For the first time in 20 years, a spacecraft dares to get so close to Io that we will be able to see up close a world of extreme volcanic activity. Juno's approach is not just a routine flyby, but a bold immersion into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons as it approaches Io's rugged surface to within 930 miles. Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io and took some incredible images. In them, Jupiter's moon appears to shine with sulfuric tones, and its surface is dotted with spots created by the volcanic activity that plagues it. Combining the data from this flyby with our previous observations, the Juno scientific team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We're looking for how often they erupt, their brightness and temperature, how the shape of the lava flow changes, and how Io's activity is related to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam camera continues to take spectacular images despite the challenges posed by Jupiter's intense radiation. The Star Navigation Camera, which is also a scientific instrument, provides the highest resolution images of Io's surface obtained to date on Earth. Scientists are studying the data coming from Juno. Each piece of data is a piece of the puzzle that reveals new information about Io's volcanic nature. Analyzing this is like a window into the past, present, and future of our solar system. Late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one taken on December 30th stands out, vividly showing Io's volcanic nature. This image, enhanced to highlight details, shows a volcanic plume erupting from the surface with plumes reaching more than 60 m, considering that the moon's diameter is about 2,200 m. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the other 95 moons of the planet, Io stands out not only for its proximity to Jupiter, but also for the spectacular geological activity that this proximity causes. The moon's volcanic nature is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It is only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and compresses Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, but more closely resembles an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter as it approaches the planet. Its gravity stretches it and, as it moves away, compresses it. This constant stretching creates tremendous internal heat that gives rise to intense volcanic activity. This JunoCam image captures a plume of material ejected from the Prometheus volcano, indicated by the red arrow. The plume is barely visible in the darkness under the terminator, the line that divides day and night. The image was taken by the spacecraft on October 15, 2023. The tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat gives rise to the volcanic activity that characterizes Io's landscape. Hundreds of volcanoes at the surface, some of them launching lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io. About 150 are erupting at any time. But Jupiter is not the only protagonist in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert influence on Io. Their gravitational attraction helps maintain Io's elliptical orbit, so they play a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determines a moon's fate. The tidal forces of Jupiter and its moons not only heat Io, but create a world where geological activity is the norm, not the exception. This moon wrapped in fire and sulfur plays a key role in the Jupiter system's great theater. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes of the satellite are the most active in the solar system, and in doing so expel enormous amounts of sulfur dioxide, or SO2, into space. This is a direct result of intense internal heating and contributes to an atmosphere rich in sulfur compounds. But the influence of Io extends far beyond its own atmosphere, since, by rotating within the enormous magnetosphere of Jupiter, sulfur dioxide and other volcanic gases are ionized and become charged particles. These particles are trapped in Jupiter's magnetic field, forming a plasma called the Io torus along Io's orbit. This torus, a bright ring of ionized particles, is a direct manifestation of the moon's volcanic power. The torus plasma is not a static feature, but changes in response to the expulsion of material from the volcanoes, feeding the torus and affecting its density and composition. This complex interaction between Io's volcanism and the torus plasma illustrates the interconnection of the Jupiter system. It is also believed to be responsible for the powerful permanent auroras at the planet's poles. The volcanic emissions, once in the atmosphere, escape into space, where they undergo rapid neutralization, a process that expels these particles at high speed in a plane perpendicular to the local magnetic field. This phenomenon continues until the formation of extended sodium nebulas, which add another layer to the complex environment surrounding Jupiter. Observational studies have been crucial in shedding light on these interactions for years. Telescopes like TRAPPIST have followed the variability of the Io sodium cloud. These observations have shown that the physical properties of Io's sodium jets are highly variable and, curiously, do not always correlate directly with the global brightness of the Jupiter plasma or with the extended sodium nebula. This study highlights the complexity of the coupling between the surface atmosphere and the magnetosphere in the Jupiter system. Current research aims to reveal the precise mechanisms by which the volcanoes of Io supply material to the torus plasma, and how the sodium jet of Io contributes to filling the plasma deposits of the magnetosphere. Therefore, the incessant volcanic activity of Io and its interaction with the magnetic fields of Jupiter are not only isolated phenomena, but play a fundamental role in shaping the dynamics of the magnetosphere of Jupiter, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io's exploration is about to reveal secrets that have remained hidden beneath its stormy surface for centuries. We present the Jupiter Icy Moons Explorer mission, abbreviated as JUICE, which aims to study Jupiter's icy moons, offering exciting opportunities to advance our understanding of Io. Although the main objective of JUICE is Ganymedes, Europa, and Callisto, its extensive set of instruments can provide valuable information about the dynamic environment of Io. The dynamic environment of Io. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center by the European Space Agency. The spacecraft is expected to arrive at Jupiter in July 2031, after 4 gravitational assists and an 8-year journey. As JUICE traverses the Jupiter system, its trajectory could offer opportunities to observe Io. These encounters could provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions aimed directly at Io. Equipped with sophisticated instruments designed to study magnetic fields, the plasma environment, and atmospheric composition, it can indirectly expand our knowledge of Io by studying Jupiter's magnetosphere. The Io Volcano Observer, IVO, mission is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO was a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geological dynamism. IVO's mission is to enter orbit around Io and perform multiple close flybys equipped with state-of-the-art instruments. IVO will map Io's surface and take high-resolution images of the surface, as well as the atmosphere, its intense volcanic activity, its subsurface structures, and the complex processes that drive its geological dynamism. IVO's mission is to enter orbit around Io and perform multiple close flybys equipped with state-of-the-art instruments. IVO will study the composition of the lava and probe the internal structure of the moon. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the EVO mission is the exploration of the bowels of the moon. What lies beneath its fiery facade? EVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis could reveal the presence of magma chambers and provide information about the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. EVO's observations could revolutionize our understanding of volcanic processes not only on Io, but throughout the solar system. By studying Io's unique volcanism, we can better understand the thermal evolution of planetary bodies and the role of tidal forces in the formation of planetary geology. Meanwhile, Juno continues to work with many more planned observations, not only of Io, but also of the other Galilean moons and, of course, of Jupiter itself. The spacecraft will continue operating until September 2025 or until it breaks down, whichever comes first. Meanwhile, we will eagerly await more images from the next flyby. Music! Have you ever heard of a galaxy that defies classification? Imagine a cosmic structure combining an ancient, golden core with a bright halo of young stars. This is not a typical spiral or elliptical galaxy, but something far more mysterious, a Hogue object initially mistaken for a planetary nebula or gravitational lens. The true nature of the Hogue object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue and teeming with new star formation. A clear separation separates the two components, as if they belong to different galaxies. The object has an impressive extension of 121,000 light-years wide, with a central core of about 17,000 light-years in diameter and an outer ring that extends 75,000 light-years. This apparent separation between the core and the ring is wider than the ring itself, which is surprising for such a colossal galaxy. Ring galaxies, such as the Hogue object, are extremely rare and account for less than 1% of all known galaxies. They often arise from complex cosmic events, but the Hogue object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of this galaxy's origin. Was it the result of a quiet accretion process, or was it influenced by a cosmic collision? Arthur Hogg, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and baffle scientists for decades. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, which was later named after him, had characteristics unlike any previously observed galaxy. At first glance, the Hogue object appeared to be a planetary nebula, a cloud of gas and dust around a dying star. However, its unusual structure, formed by a central core surrounded by a luminous ring, suggested otherwise. The first images taken by the astronomer's telescope showed a clear separation between the internal and external components, which aroused curiosity and speculation. The initial hypotheses varied widely. Hogg himself hypothesized that it could be a planetary nebula or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy, but a huge elliptical galaxy magnifying a background galaxy in the form of a ring. Gravitational lenses occur when a massive object, such as an elliptical galaxy, deflects light from a more distant object behind it. This curvature creates a ring of light around the foreground object, known as an Einstein ring. In early observations, the outer ring of the Hogue object resembled such a lens, suggesting that it could be a foreground galaxy amplifying the light from a more distant object. For nearly 4 decades, the true nature of the Hogue object remained uncertain. It was not until 1987 that astronomers, equipped with improved technology, were able to confirm the connection between the ring and the core by spectroscopic analysis of the redshift. This redshift is due to the expansion of the universe, and more distant objects exhibit a greater redshift. By analyzing the redshift of the core and ring of the Hogue object, astronomers confirm that they are not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and consolidated the status of the Hogue object as a unique type of galaxy. The central core, formed by old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguish the Hogue object from typical spiral and elliptical galaxies. Ring galaxies are rare and account for less than 1%. The Hogue object, with its perfectly separated core and ring, remains one of the best defined examples of this rare class of galaxies. The discovery initiated a scientific journey to understand one of the most mysterious structures in the universe. With the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its calm appearance and the clear separation and combination of an ancient core with a ring of young star formation make the Hogue object a unique and enigmatic galaxy that has led astronomers to investigate various theories about its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hogue object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. When a smaller galaxy collides with a larger one, the impact generates a density wave that expands outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring that surrounds the galaxy's core. The Cartwheel Galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hogue object, if a smaller galaxy collided with it, one would expect to detect several key features. First, the collision would create density waves that would push the gas and stars outward, forming a ring. In addition, the stars in the ring should have shown high relative velocities, indicating the kinetic energy of the collision. And third, there would be residual fragments or remnants of colliding galaxies in or near the ring. Of the colliding galaxies. However, detailed observations of the Hogue object have revealed some inconsistencies with the collision hypothesis. The stars in the ring do not show the high relative velocities typically associated with this type of event. In addition, a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galactic collisions have been used. These models show that all collisions can produce a ring structure, but the resulting galaxy usually retains traces of a violent interaction. The Hogue object, which has a calm and symmetrical appearance, lacks these chaotic characteristics, suggesting a more complex formation history. However, another intriguing possibility looms: the resonance theory. Could the ring structure of a galaxy be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hogue object is resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of internal dynamics in barred spiral galaxies. In particular, due to the resonance in the gravitational field, spiral galaxies are characterized by the structure of a central bar from whose in-spiral arms branch off. These bars play a key role in the dynamics and evolution of galaxies. According to the theory, as the bar rotates, it can create resonance affecting the distribution of gas and stars in the galaxy. Resonance occurs when gravitational forces within a galaxy create regions where the rotational speeds of gas and stars synchronize. These regions can trap gas and stars, which leads to ring formation. There are several basic types of resonances. The internal Lindblad resonance occurs near the center of a galaxy and often forms an internal ring. The external Lindblad resonance arises further away and can form an external ring. The third type is the corotation resonance, a region in which the rotation speed of the bar coincides with the orbital speed of the stars and gas. And this can also lead to the formation of rings. In the case of the Hogue object, the presence of a ring around the elliptical nucleus suggests these resonances may have played a role in its formation. The bar structure could have caused resonance that trapped gas and stars at certain radii, creating the distinctive ring we observe today. When the bar rotates, it exerts a gravitational influence that can reorganize the galaxy's gas and stars over time. This process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism explaining how a spiral galaxy can evolve into a ring galaxy without collisions. NGC 1291 is a classic example of a galaxy in which the effects of resonance likely played a role in the formation of the ring. The central band and outer ring provide a visual analogy of what may have occurred in the Hogue object. However, resonance theory faces difficulties when applied to the Hogue object. Specifically, the Hogue object does not currently have a central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there's another interesting and equally plausible theory, accretion theory. Can the gradual accumulation of intergalactic gas explain the galaxy's unique structure? Let's explore this in more detail. The third important theory proposed to explain the formation of the Hogue object is accretion theory. According to this theory, the unique structure of the galaxy is the result of the gradual accumulation of intergalactic gas, rather than a dramatic collision or an internal resonance. Accretion is the process by which a galaxy collects gas over a long period of time from the surrounding intergalactic medium. This gas is dragged by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hogue object, a central elliptical nucleus likely formed first over time. The gravity of this nucleus attracted gas from the intergalactic medium, and as the gas approached the nucleus, it began to rotate around it, forming a ring structure due to the conservation of angular momentum. As the gas accumulated in the ring, its density reached a level high enough to trigger star formation. This process explains the ring's bright blue color, which indicates ongoing active star formation, and the space between the nucleus and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies like NGC 6028 are an example of how accretion can lead to ring structure formation. These galaxies show similar characteristics: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While accretion theory offers a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How do the dynamics of gas inflow and star formation create such a clear separation between the nucleus and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence supporting this theory. The Hogue ring object contains more gaseous mass than the entire Milky Way, suggesting a significant accretion of intergalactic material. In addition, the ring's well-defined structure and the absence of chaotic debris are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory by modeling the gravitational interaction in such ring systems. Scientists have demonstrated how the balance of forces can create stable and unstable orbits that lead to discontinuities in mass distribution. These results are consistent with the observed structure of the Hogue object, where the space between the nucleus and the ring is a region of unstable circular orbits, further supporting the theory. In addition, accretion theory offers a fairly compelling explanation of the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has its own flaws, leaving several questions unanswered. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object or the absence of residual fragments and the high relative velocities that are commonly observed in this type of events. The resonance theory, on the other hand, suggests that internal gravitational resonances within a warped spiral galaxy can create ring-shaped structures. However, it is clear that the Hogue object lacks the central bar necessary for this process, and the theory does not fully explain the apparent space between the nucleus and the ring. The accretion theory lacks the central bar necessary for this process, and the theory does not fully explain the apparent space between the nucleus and the ring. The accretion theory, for its part, argues that the gradual accumulation of intergalactic gas forms a ring, which explains the ordered structure and ongoing star formation. However, questions arise as to why the ring forms at a particular radius and how the dynamics between the nucleus and the ring create such a distinctive space. Despite these theories, several mysteries remain. Why is there a significant space between the nucleus and the ring? The nucleus and ring. What specific conditions led to the formation of such a defined structure, and how do gravitational forces and dynamics within the galaxy interact to maintain its balance? Future telescopic missions, such as the Nancy Grace Roman Space Telescope and the extremely large telescope soon to be launched, are designed to provide a deeper understanding of these issues. These advanced observatories will provide higher resolution images and more detailed spectroscopic data that could reveal the underlying processes in the formation of this type of ring galaxies as we explore the cosmos. The object remains a testament to the diverse and complex processes that form galaxies and reminds us that there are still mysteries to be discovered in the cosmos. Imagine a particle so elusive that trillions pass through you every second without a trace. A particle born in the burning hearts of stars, in the cataclysmic collapse of a supernova, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space that carry secrets that could rewrite the laws of physics. But why are they so difficult to detect? And what secrets can they reveal if we finally learn to listen to their whispers? By immersing ourselves in the realm of these ghostly particles, we delve into the territory where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. Music. The history of the neutrino begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was an era in which the universe revealed its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem in beta decay, a type of radioactive decay observed in atomic nuclei. Energy seemed to disappear, which contradicted the principle of conservation of energy, one of physics' most fundamental laws. Pauli proposed a radical idea. What if the missing energy was carried by an undetectable particle? He tentatively called this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was instrumental in developing a theory that described this elusive particle and consolidated its place in the scientific lexicon. Let's travel back to the Cold War era, a time in which science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the focus of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not limited to military power, but extended to the realm of science, where both sides sought advances that would give them an advantage. One of these stories is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some of them carried out in underground depths, in abandoned mines, or in remote locations, where scientists tried to capture these ghostly particles. Neutrinos, although among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that it was long thought to be zero. Unlike other fundamental particles, neutrinos only interact through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it does not exist. Right now, trillions of them are passing through you without you detecting them. There are three known types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino, each associated with a corresponding charged particle. The electron, the muon, and the tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery, as it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can transition between these mass states, leading to a change in flavor. This discovery not only won the Nobel Prize in Physics in 2015, but also highlighted the gaps in the standard model, changing our understanding of fundamental physics. Neutrinos also play a key role in some of the most dramatic processes in the universe. In the heart of a star, nuclear reactions generate enormous amounts of neutrinos that leave the star almost instantaneously, carrying away energy. Neutrinos are the first particles emitted from a dying star, indicating the beginning of supernova. These particles provide crucial information about the processes taking place in the core long before light can escape. When a massive star reaches the end of its life cycle, its core collapses, triggering a supernova explosion. During this cataclysmic explosion, a huge amount of neutrinos is produced, of magnitudes greater than the energy emitted by light. These neutrinos leave the supernova almost instantaneously, propagating through space, and some end up reaching Earth, allowing us to glimpse these violent events. It is also speculated that neutrinos could be related to one of the greatest mysteries of astrophysics, dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino that does not interact with any known fundamental force except gravity, could constitute dark matter, the invisible mass that makes up most of the matter in the universe. Although this remains a field of intense research, the possibility that neutrinos may unlock the secrets of dark matter underscores their importance in our quest to understand the cosmos. Thus, the search for high-energy neutrinos has led scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica is the Ice Cube Neutrino Observatory, which scans the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events still shrouded in mystery. Recent research has begun to unravel this mystery, pointing to active galactic nuclei, or AGN, as significant sources of these high-energy neutrinos. AGN are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases enormous amounts of energy, often forming jets of particles at high speed. However, recent discoveries show that these jets may not be the only neutrino source. In 2022, the galaxy NGC 1068 was identified as a possible source of high-energy neutrinos, a discovery that surprised many scientists. The neutrinos were traced to the galaxy's nucleus, where a supermassive black hole hides behind thick layers of dust and gas. This discovery refuted the popular belief that these neutrinos can only be emitted by galaxies with bright quasars, like blazars. The surprises do not end with NGC 1068. Subsequent studies revealed two other galaxies, NGC 4151 and NGC 3079, as possible sources of high-energy neutrinos. The findings strongly suggest that the environment surrounding the supermassive black holes of these active galaxies is a powerful neutrino factory. These findings have triggered a paradigm shift in our understanding of the origin of high-energy neutrinos. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but there are other projects on the horizon that aim to expand further the limits of our knowledge. In Japan, the Hyperchemio Candy is about to become a leader in neutrino detection. This huge underground detector, located in a cave excavated especially for this purpose, will be filled with 260,000 tons of water. The goal is to capture the fleeting flashes of Cherenkov radiation that occur when neutrinos interact with water molecules, a technique perfected over decades of Japanese research. Meanwhile, in the United States, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will use a state-of-the-art time projection chamber in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map the properties of neutrinos in great detail. Although both Hyper-K and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K relies on proven technologies and aims at massive data collection. DUNE, on the other hand, relies on innovative technologies that may reveal new aspects of neutrino behavior. There's a lot at stake. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which could explain why the universe is mainly composed of matter rather than antimatter. CP parity violation could be the key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it by comparing the oscillations of neutrinos and their antimatter and neutrinos as they traverse space. These detectors can show whether there is a fundamental difference in the behavior of matter and antimatter, but the race to find CP parity violation is also a race against time. Hyper-K is expected to begin collecting data as early as 2027, which could give it an edge over Dune, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, as it provides a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more evident than in the study of neutrinos. These elusive particles, which hardly interact with other matter, have properties that extend the limits of our knowledge. One of the most important challenges for the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to have no mass, but the observation of neutrino oscillation, when they change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model, but that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model, as they suggest the possible existence of a new type of neutrino, the sterile neutrino. We have already mentioned it in passing, but here is the essential. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos only interact through gravity, which makes them even more difficult to detect, but their existence could explain several mysteries of physics. If sterile neutrinos are proven to exist, they would not only call into question the completeness of the Standard Model, but would open the door to a completely new physics. This would require expanding the model to include these new particles, which could lead to a more unified theory of fundamental forces. Neutrinos could also provide clues about another profound mystery: the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is scarce. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos break this symmetry, this could explain why there is more matter than antimatter after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence of CP symmetry violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185 to 300 kilometers journey across Japan to the Super Kamiokande detector for nearly a decade. Researchers have observed that neutrinos oscillate to different types more often than antineutrinos, suggesting that they may behave differently. This possible violation of CP symmetry in neutrinos could be the missing piece to explain why the universe is mainly composed of matter. However, the current results, although promising, are not yet conclusive. The level of statistical significance needed to recognize a discovery in particle physics is 5 sigma, and the results of the T2K have only reached approximately 3 sigma, which means that, although the evidence is solid, it is not absolute to truly confirm CP violation in neutrinos and unlock the secrets of antimatter. Scientists are turning to the next generation of neutrino detectors, Hyper-K in Japan and Dune in the United States, which are ready to take this research to the next level. These huge detectors will collect much more data with greater precision, being able to reach the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science. Why is there something instead of nothing? The study of neutrinos, once considered an obscure branch of physics, could end up being the key to understanding the very structure of our reality. To answer some of the deepest questions in physics, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or KATRIN, in Germany. The KATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the minuscule mass of neutrinos by analyzing the energy of the electrons emitted in this decay. Cochrane aims to establish an upper limit for the mass of neutrinos, expanding the limits of discernibility. Cochrane has already achieved significant advances, establishing an upper limit for the mass of neutrinos of 0.8 electron volts, with a sensitivity of up to 0.2 electron volts. However, this may not suffice to determine the real mass of neutrinos, which could be even smaller. This finding has triggered a global effort to develop alternative methods and experiments that can surpass the capabilities of Cochrane. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays by electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected with extremely sensitive equipment. Experiments with holmium-163 have already demonstrated very precise energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the experiment of Project 8, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could exceed the limits established by cosmological studies and provide crucial data on the real mass of neutrinos. The search to understand neutrinos is not limited to one country or continent. It is truly a global effort. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration beyond borders, while we await the first signals from Japan, which is already taking shape in a newly excavated cave, and news from Dune, nestled deep within an old gold mine in South Dakota. The next chapter in our understanding of the universe is just beginning. Stay tuned as we travel through the frontiers of science, making one discovery at a time. The more we delve into the universe, the more mysteries it reveals to us. Gravity, the invisible force that binds the cosmos, may not be as immutable as we thought. From ancient civilizations to Einstein's revolutionary discoveries, our understanding of gravity has constantly evolved. However, recent discoveries suggest that there could be a large-scale cosmic failure, a subtle deviation in the force that governs galaxies and stars. Ancient scientists pondered the nature of gravity, laying the foundations for Newton's elegant laws, but it was Einstein, in the early 20th century, who changed our perception. His theory of general relativity describes gravity not as a force, but as a curvature of space-time itself. Despite its success in predicting phenomena, such as black holes and gravitational waves, Einstein's theory has its limitations. When we turn our gaze to the scale of galaxy clusters and beyond, we find inconsistencies. Gravity seems to weaken slightly over billions of light years, and this phenomenon, which researchers now call cosmic failure, could point to a new physics, perhaps an extension of the standard cosmological model that includes a variable gravitational constant. Such a modification could reconcile these inconsistencies without overturning the established successes of general relativity. The discovery of cosmic failure forces us to rethink our understanding of gravity. Could this be the first clue to a new puzzle that will ultimately lead us to a theory that unifies the fundamental forces of nature? Long before the scientific revolution, ancient civilizations had already encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, in which the Earth was the center of the universe. Aristotle argued that objects fall towards their natural place, and this theory dominated Western thought for centuries. In ancient India, Hindu scriptures describe the concept of gravity as an inherent force that attracts objects to Earth. Similarly, the Chinese philosopher Mozi, in the 4th century A.D.C., suggested that objects fall due to the force of the Earth's energy. These early ideas, although primitive by modern standards, laid the foundation for future scientific research. It was not until the Renaissance that a more accurate understanding emerged. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for the pioneering work of Isaac Newton. Newton's formulation of the law of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other in proportion to their masses and inversely proportional to the square of the distance between them. This elegant equation unified the sky and the earth under a single universal law. In the early 20th century, Albert Einstein revolutionized our understanding of gravity by proposing the general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equation suggested that massive objects, such as stars and planets, warp the fabric of space-time, creating what we perceive as gravity. This concept was visually confirmed during the 1919 solar eclipse expedition led by Sir Arthur Eddington. By observing the curvature of starlight around the sun, Eddington provided one of the first experimental confirmations of the general theory of relativity. Consider this, almost a century ago, Einstein added an adjustment factor to his equations to fit the then-accepted idea of a static universe, and later called this factor his biggest mistake. However, this lambda constant reappeared many years later to explain the accelerated expansion of the universe. Einstein's theory also predicted phenomena, such as black holes and gravitational waves, which we have only begun to observe in recent years, further confirming the validity of his theory. The image of the event horizon of a black hole captured by the Event Horizon Telescope of a black hole in 2019 and the detection of gravitational waves by LIGO in 2015 were monumental achievements in modern astrophysics. However, despite its successes, general relativity has its limitations, as it is incompatible with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to seek a more complete theory that unifies these two pillars of physics in the search to understand the universe. Scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, while solid, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has had remarkable success in explaining a wide range of phenomena, from planetary orbits to the behavior of light near massive objects. However, recent investigations point to possible inconsistencies when the general theory of relativity is applied at cosmic scales. Recent investigations by Robin W. Chwyw and his colleagues in 2024 raise the hypothesis of a cosmic failure in gravity. Their research suggests that the gravitational constant might not be exactly constant at large cosmic distances. In particular, gravity appears to be about 1% weaker when dealing with distances of billions of light years. This anomaly causes difficulties in understanding what is happening, as it implies a deviation from Einstein's theory on extreme scales. To solve this problem, scientists propose a modification of the standard cosmological model known as lambda-CDM. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on a cosmic scale without affecting its proven precision on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. General relativity best describes large-scale structures, such as galaxies and black holes, while quantum mechanics provides the best framework for understanding particles at the smallest scales. However, the two theories are fundamentally incompatible. One of the most striking tests of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the center of black holes. In contrast, quantum mechanics suggests that such infinities cannot exist, indicating the need for a new theory that can unify the two. Recent technological advances, such as precise measurements of the cosmic microwave background by the Planck satellite, have provided new data that both confirm and refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity must be revised. The cosmic failure theory, which introduces a small change in the gravitational constant, offers a possible solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from the general theory of relativity that could not be detected before. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. Experiments carried out at CERN, at the Large Hadron Collider, aim to explore the limits between these two areas, seeking evidence that can bridge the gap between general relativity and quantum mechanics. In the search to understand gravity, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon arising from deeper principles. This idea does not contradict traditional ideas about gravity, but opens new avenues of theoretical research. A well-known alternative is modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the early 1980s. The theory suggests that Newton's laws need adjustments at the very low accelerations characteristic of the outskirts of galaxies. According to MOND, these changes can explain the rotation curves observed in galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it is unable to explain large-scale cosmic phenomena, such as galaxy clusters and the cosmic microwave background, where dark matter remains a more accepted explanation. Another interesting theory is emergent gravity, proposed by Eric Verland in 2010. Verland suggests that gravity is not a fundamental interaction, but arises from thermodynamic principles of information storage on holographic screens. From this point of view, the universe can be described as a hologram in which gravity arises from changes in entropy associated with information stored on these screens. To simplify, imagine the universe as a giant laboratory in which books containing information are stored on shelves, which are holographic screens. The arrangement and number of books change over time, which affects the overall structure and creates what we consider gravity. Emergent gravity has intriguing implications for our understanding of dark matter. Instead of invisible particles, the effects attributed to dark matter could be a consequence of the emergent properties of space-time itself. This theory allows us to take a new look at the connection between gravitation and thermodynamics. In addition to the theory of Mond and Verland, there are other alternative approaches. One of these theories is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galactic clusters without dark matter. MOG suggests that these additional fields modify the force of gravity on different scales. In addition, the concept of entropic gravity, closely related to Verland's ideas, suggests that gravity arises from the tendency of systems to increase entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics and provides a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open new perspectives for us and require further research and experiments. They force us to reconsider the vision of gravitation, not as a force inherent in nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our quest to understand gravity continues to push the boundaries of technology and knowledge. Cutting-edge experiments and missions are being designed to test the limits of our gravitational theories, providing us with new insights and potentially revolutionary discoveries. One of the most important ongoing projects is, of course, the acclaimed James Webb Space Telescope, JWST. The observations made to date have been crucial to testing theories of gravity on a large scale, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle accelerator, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the possible discovery of particles that may mediate the gravitational interaction at quantum scales. The LHC experiments are fundamental to understanding how gravity can be combined with other fundamental forces. Space missions, such as the Laser Interferometric Space Antenna LISA, are also looming on the horizon, with its launch scheduled for the mid-2030s. LISA consists of 3 spacecraft that form a giant triangular interferometer in space. This facility will detect gravitational waves with much greater sensitivity than existing terrestrial detectors, such as LIGO and Virgo. LISA's goal is to observe gravitational waves from the fusion of supermassive black holes, which will test Einstein's general theory of relativity and provide new insights into dark matter and dark energy. But closer to home, the Event Horizon Telescope continues to make revolutionary contributions since 2019. The EHD obtained the first image of the black hole M87, demonstrating the power of synchronizing telescopes around the world to create an interferometer the size of an airplane. The EHD is now focusing on even more precise observations of black holes, including the one at the center of our galaxy, Sagittarius A star. These observations will test the predictions of the general theory of relativity in extreme gravitational fields. Let us remember the recent study already mentioned by Wen et al., which proposes a cosmic anomaly in gravity that suggests that the gravitational constant may vary along cosmic distances. This study will be tested with data from the Planck satellite and future experiments on the cosmic microwave background. Upcoming missions, such as the Simon Observatory and CMBS-4, aim to make more accurate measurements of the CMB that may confirm or refute the existence of such an anomaly, allowing for a better understanding of the nature of gravity at the largest scales. In addition, the Vera C. Rubin Observatory, which will soon be fully operational, will conduct the Legacy Survey of Space and Time. This study will map billions of galaxies, providing a detailed view of the structure and evolution of the universe. The LSSD data will help test theories about dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity through laboratory experiments. These experiments use highly sensitive equipment to detect tiny gravitational effects at very small scales, where quantum mechanical effects become significant. These experiments are designed to bridge the gap between general relativity and quantum mechanics, which could lead to a unified theory of gravitation. These cutting-edge experiments and missions represent the state-of-the-art in gravitational research. They're designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and technology. The anomalies and alternative theories we have studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant advances in several key areas of cosmology. A more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. The studies suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant advances in several key areas of cosmology. A more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently over vast cosmic distances, it could provide a new explanation for the accelerated expansion of the universe and the distribution of galaxies. This could lead to a unified model of the cosmos that better integrates general relativity and quantum mechanics. For astrophysics, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments by accurately describing the behavior of matter under intense gravitational fields. We can better understand the life cycle of stars and the dynamics of galaxies. This knowledge could even reveal new types of objects or astrophysical phenomena. Technological advances in the understanding of gravity will undoubtedly drive innovations in various fields. For example, accurate measurements of gravitational waves can improve navigation systems and geophysical research. In addition, advances in quantum gravity could lead to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Imagine a future in which our understanding of gravity allows for ultra-precise space-time sensors that lead to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we await the launch of new missions, projects, and discoveries, the anticipation grows. Each step forward brings us closer to unraveling the mysteries of the universe, promising a future in which our understanding of gravity and the cosmos is richer and deeper than ever. Imagine a colossal and invisible force at the heart of a galaxy that controls its existence. This hidden driver is none other than a supermassive black hole. Although often described as chaotic, all-devouring monsters, these giants play a crucial role in the life cycle of galaxies. At the center of most large galaxies is a supermassive black hole whose gravitational force is so strong that not even light can escape it. However, they actually do much more than absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways we are only beginning to understand. Recent research shows that the jets of gas and radiation expelled by the poles of supermassive black holes are similar to the airways that feed our lungs. These jets create shock waves that oscillate in much the same way as the thoracic diaphragm of our chest cavity, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from becoming too large and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how the heart and lungs of a galaxy in the form of columns of gas from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full of zombie galaxies, enormous clusters of dead or dying stars. The shock waves generated by the jets of black holes can prevent the formation of stars by heating the surrounding gas and preventing it from cooling and condensing to form new stars. This process may seem destructive, but it is necessary for maintaining the health and longevity of galaxies. Today, we will try to understand the mysterious nature of supermassive black holes. We will learn the profound impact they have on the universe, and, in the end, realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass between 8 and 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar black hole. These black holes usually have a mass several times greater than the Sun's. Another way is the direct collapse of massive gas clouds, which completely omits the stellar formation stage. This process can lead to the formation of black holes with masses ranging from thousands to hundreds of thousands of solar masses. It is believed that these direct collapses occurred in the early universe and were the origin of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of Einstein's general theory of relativity. These equations describe how matter shapes the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape. The first black hole confirmed by observations was Cygnus X-1, discovered in 1964. This stellar mass black hole in the Milky Way was identified by X-ray emission caused by material accretion from a companion star. This discovery was the first compelling evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the limit beyond which nothing can pass. Once inside its limits, the photon sphere is a region where gravity is so strong that light particles are forced to orbit the center. There, a singularity exists, a point of infinite density where the laws of physics, as we know them, break down. Black holes come in various sizes. Stellar mass black holes form from the collapse of stars and have masses several times greater than that of the Sun's supermassive black holes. Located in the center of most galaxies, have masses ranging from millions to billions of solar masses. Less common, intermediate mass black holes fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration captured the first image of a black hole located in the M87 galaxy. In this historic image, the shadow of the black hole can be seen against a bright accretion disk. The observation provided direct visual confirmation of theories about black holes and opens new possibilities for studying these mysterious objects. One of the most common and debated questions lately about black holes is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon. One falls into the black hole, and the other flies away for an incredibly long period. This trick of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are depicted in science fiction, they are not cosmic vacuum cleaners that indiscriminately absorb everything around them to hit them. Objects must get incredibly close to the event horizon. Furthermore, although it has been proposed that black holes are possible wormholes or portals to other universes, these ideas remain speculative and are not supported by observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the fundamentals of black holes, how they form, their different types, and key discoveries, lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is noticeable by the enormous gravitational forces they exert on their environment. But how do these colossal formations arise, and what are their defining characteristics? In theory, a black hole forms when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful nothing can escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive ones, are scattered throughout the universe, and their number may be in the billions. Massive are scattered throughout the universe, and their number may amount to billions. Supermassive black holes, with masses millions or billions of times greater than the Sun, are detected thanks to their gravitational influence on nearby stars. These stars orbit the black hole much faster than they would around a normal object of similar mass. By measuring these orbital speeds, astronomers can estimate the black hole's mass. For example, the black hole located in the center of our Milky Way, Sagittarius A*, has a mass of approximately 4 million solar masses. Some supermassive black holes even surpass Sagittarius A*. The dwarf galaxy Leo 1 contains a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with an astonishing mass of 55 million solar masses, and even more colossal is a black hole in the galaxy cluster 2261, whose mass is estimated at about 100,000 million solar masses, although its exact location remains unspecified. These black holes, especially in active galaxies, behave differently. Surrounded by an accretion disk of gas and dust that rotates rapidly, they can emit enormous amounts of energy, sometimes eclipsing their entire galaxy. This same process was captured spectacularly by the Event Horizon Telescope in 2019, when it photographed the accretion disk around the supermassive black hole of Messier 87, revealing the ominous shadow of a black hole with a mass of 5,000 million solar masses. The formation of these supermassive black holes is a subject of intense study and speculation. Unlike the vacuum cleaners in science fiction stories, real black holes attract matter by gravity, not by active suction. This gravitational attraction becomes unusually strong at short distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds containing as much matter as millions of stars. This direct collapse model suggests that these black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes, born in the extreme conditions of the Big Bang, served as seeds for subsequent growth. By studying these colossal formations, we can understand the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? Music. It is not just a dramatic cosmic event, but a transformative process that changes the very structure of the universe. At the center of these galactic collisions are the same supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable fusion. This process is not silent, but sets in motion enormous amounts of gas and dust, creating a turbulent environment conducive to extraordinary phenomena. Physicists have modeled these colossal collisions and discovered that, as black holes spiral closer, they can produce jets of incredibly energetic electromagnetic radiation that shoot out along the axis of rotation with much more power than those normally observed around isolated black holes. The cosmic spectacle begins even before the black holes completely merge, offering astronomers a possible warning of these events. When these supermassive black holes finally collide, their jets combine into a single high-energy explosion that may be accompanied by less directional explosions, increasing the chances of detection. The fusion process sets the surrounding plasma in motion, causing powerful jets that, in theory, can be observed from billions of light years away. The detection of these cosmic events is not only exciting, but offers a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can reinforce the current understanding of gravity or open new avenues in physics that lead to alternative theories. Future missions, such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to locate these mergers. LISA, a joint project of NASA and the European Space Agency, will orbit the Sun and detect the gravitational waves emitted by these mergers. The combination of gravitational wave data with electromagnetic observations will allow us to precisely locate and study in detail these energetic events. Until these advanced instruments come into operation, astronomers depend on existing observatories to detect electromagnetic jets, which provide a dynamic vision of the evolution of galaxies and demonstrate how these mergers can drastically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A*, which has 43 million times the mass of the Sun. In mid-spring this year, the giant of our galaxy revealed new secrets thanks to advanced observations from the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A*, providing new insights into the magnetic field surrounding this black hole. Polarized light is crucial for understanding these fields, as it shows how light waves are oriented and allows us to understand the properties of a gas and the mechanisms that act in the feeding of the black hole. Interestingly, the magnetic field around Sagittarius A* are surprisingly similar to those observed around the much larger black hole in the Messier 87 galaxy, which has a mass of 65 billion times that of our Sun. This similarity suggests that strong and organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes intriguing the possibility that Sagittarius A* may contain a hidden jet. In other black holes, these fields drive powerful currents of matter, although Sagittarius A* appears relatively calm and consumes a minimal amount of matter. The similar structure of its magnetic field points to the possibility of a weak jet that has not yet been observed. This new image of a black hole in the center of the Milky Way tells us that there are strong rotating and ordered magnetic fields near the black hole, explains Sarah Issoun, co-director of the study and fellow of the NASA Hubble-Einstein program at the Center for Astrophysics of Harvard and Smithsonian. These fields are crucial for the way black holes interact with the gas and matter that surrounds them. It was the EHD, a set of telescopes from around the world, that made these revolutionary observations possible by combining data from multiple telescopes. The EHD forms a virtual telescope in the shape of the Earth, capable of capturing unprecedented details of black holes. Although Sagittarius A* is closer, it presents a unique challenge due to its smaller size. The material that rotates around it moves rapidly, making it difficult to obtain sharp images. In contrast, in a larger M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data to compare black holes at opposite ends of the mass spectrum. The similarity observed in the magnetic fields between Sagittarius A* and Messier 87 suggests that the central black hole of our galaxy could have a hidden jet. If it existed, it would provide new insights into the behavior and evolution of black holes and the galaxies in which they are located. The observation of this jet would be a great discovery that would relate Sagittarius A* to the energetic processes that form galaxies. The discovery of such a jet would greatly expand our understanding of how black holes affect their environment. Jets can expel gas and dust, which affect star formation and the overall evolution of galaxies.